Our entire universe and existence is built up of atoms. They are like the building blocks of everything we know. But how did atoms form in the first place? Where did they come from? Our understanding of atoms is that they are extremely tiny, but could the entire universe somehow be one single atom? Picture an atom in your mind. It's like a tiny hub called a nucleus, and around it there are super fast electrons zooming around. Now, let's dive into a curious thought. How do these electrons manage to keep spinning around the nucleus without slowing down? This question stirred up quite a puzzle back in the early 20th century and led to the fascinating development of quantum mechanics. Physicists were on a mission to unravel the secrets of atoms. They figured out that each atom has a nucleus, kind of like a center, with a positive charge and considerable mass. Around this nucleus there are these incredibly small electrons with a negative charge. Armed with this basic insight, scientists set out to craft a more detailed model of the atom. At first, they drew inspiration from our solar system, thinking of a dense nucleus similar to the Sun, with tinier bits like planets orbiting around it. However, this model faced a couple of big challenges. First, when charged particles speed up, they shoot out electromagnetic radiation. Now, electrons are charged and zoom around during their orbits, so according to this model, they would be constantly emitting radiation. This would mean they lose energy and quickly spiral inward, eventually crashing into the nucleus. But we know atoms stick around for way longer than a tiny fraction of a second, making this model not very practical. Second, atoms were observed emitting radiation at specific, distinct frequencies, which is different from the continuous emission expected if electrons followed the solar system model. Quite a head-scratcher, right? Niels Bohr, a highly regarded physicist from Denmark, stepped into the scene as the pioneer in resolving the perplexities surrounding electrons' behavior in atoms. It was in the year 1913 when he presented a groundbreaking idea. Electrons in an atom aren't just randomly spinning around. Instead, they are restricted to specific quantized distances from the nucleus. Bohr went further by proposing a minimum distance that an electron could stay away from the nucleus. Beyond this point, it couldn't get any closer. These concepts weren't mere hunches. They were solidly grounded in the earlier work of German physicist Max Planck. About a decade before Bohr's breakthrough, Planck introduced the idea of quantization of radiation emission. According to Planck, objects could only absorb or release radiation in distinct fixed amounts, not in any arbitrary value. These fixed amounts were defined by a constant value known as Planck's constant. Similar to angular momentum, Bohr took inspiration from Planck's work and applied it specifically to electrons whirling around a nucleus. He asserted that the smallest orbit an electron could have would possess an angular momentum exactly equal to 1 Planck constant. Larger orbits, on the other hand, could exhibit multiples of the Planck constant, like twice or 3 times its value, but they could never have fractions like 1.3 or 2.6. These intricate models laid the foundation for a more precise understanding of atomic structure, unraveling the mysteries of electrons' behavior within the microcosm. Achieving a comprehensive grasp of why electrons adopt specific orbits and adhere to well-defined energy levels necessitated the full-fledged development of quantum mechanics. Electrons, akin to other particles constituting matter, exhibit dual characteristics, acting both as particles and waves. While our conventional perception might liken an electron to a miniature planet circling a nucleus, an alternative perspective envisions it as a wave encompassing the nucleus. When waves are confined within a delimited space, they are bound by special regulations. They cannot exhibit arbitrary wavelengths, but must conform to standing wave patterns that precisely fit the given space. Consider this akin to playing a musical instrument. When you fasten the ends of a guitar string, only specific lengths produce distinct notes. Similarly, the electron wave encircling a nucleus must align with the available space, and the nearest orbit is dictated by the first standing wave of that electron. As quantum mechanics advanced, refinements were made to this model, but the fundamental concept remained consistent. An electron cannot approach the nucleus beyond a certain point due to its quantum mechanical limitations, which restrict it from occupying a smaller spatial realm. This intricate analogy, likening electron behavior to musical harmonies, offers a bridge for comprehending the fascinating interplay between quantum mechanics and the dynamic dance of particles within the microscopic realm. Another way to understand this doesn't involve quantum mechanics at all. It looks at the various energies involved. An electron orbiting a nucleus feels an electric pull towards the nucleus, always trying to get closer. At the same time, the electron has kinetic energy pushing it away. For a stable atom, these forces are balanced. The total energy of an electron in orbit, combining its eitic and potential energies, is negative, so to remove the electron, energy must be added to the atom. This is similar to planets orbiting the Sun. adding energy is needed to remove a planet from the solar system. Picture an electron falling toward the nucleus due to the electric charge, but because of quantum mechanics, it can never reach the nucleus, staying in orbit. Physics allows this because the system's total energy is negative, showing stability and holding the components together to make a lasting atom. The prevailing scientific explanation for the origin of the universe is rooted in the Big Bang theory. Imagine a tiny, infinitely dense point, often called a singularity, that contained all of the mass, energy, space, and time of the universe. Then, around 13.8 billion years ago, this singularity began to expand. It's like all of existence was packed into a small speck, suddenly bursting outward at an unimaginable velocity. This rapid expansion, known as the Big Bang, was not an explosion in the traditional sense, more like the stretching and unfolding of a cosmic fabric. In the first fractions of a second, temperatures skyrocketed to trillions of degrees, so hot that particles couldn't even hold together. Instead, they zipped around in a seething, chaotic soup of fundamental particles: quarks, electrons, neutrinos, and more. Space was expanding at an incredible rate, and as it stretched, the universe began to cool. As the universe cooled down to a few billion degrees, quarks started to stick together, forming protons and neutrons. These particles quickly gathered into the simplest nuclei, mainly hydrogen and helium, along with tiny traces of lithium. This period, called nucleosynthesis, happened within minutes of the Big Bang, and it set the initial chemical composition of the universe. But the story doesn't end there. After just a few 100,000 years, the universe cooled enough for electrons to combine with these nuclei, forging the first atoms, mainly hydrogen and helium atoms. These atoms then started to clump together under gravity, forming the first stars and galaxies. Some of these early stars became enormous and short-lived, ending their lives in spectacular supernovae that spread heavier elements across the cosmos, paving the way for planets, life, and everything else we see today. It all started with this incredible expansion from a tiny, hot, dense point. The evidence supporting this come from several observations. The most compelling is the cosmic microwave background, and faint glow of radiation filling the universe, a leftover echo of those fiery moments shortly after the Big Bang. Then there's the observable redshift of galaxies, which shows that space itself is still stretching, meaning the universe is still expanding. The distribution of galaxies and the relative proportions of hydrogen and helium also match predictions from the Big Bang's early conditions. So from that single dense point, the universe has been unfolding and evolving over billions of years into the vast, complex cosmos we explore today. The Big Bang isn't just a theory, it's our best window into how everything we see and everything we are began. Quantum mechanics shakes up the way we think about nothing, turning it from a mere void into a surprisingly active realm. When we talk about nothing in classical physics, we usually mean empty space, completely void, devoid of matter and energy. But in the quantum world, this picture dissolves into something far richer and more perplexing. At the heart of quantum mechanics is the idea that particles don't have precise positions or velocities until they're observed, and even in abundance, the vacuum isn't truly empty. Instead, it's a restless sea of fleeting phenomena known as quantum fluctuations. These fluctuations mean that virtual particles, pairs of particles and antiparticles, can spontaneously pop into and out of existence within extremely short timescales. They're like ephemeral mirages in the fabric of space itself. This quantum jittering suggests that nothing isn't quite nothing at all. Instead, it's a seething froth of energy, constantly flickering in and out of non-existence. The vacuum state in quantum field theory isn't a simple emptiness, but a ground state filled with potentialities. In fact, this ground state can contain energy, called zero-point energy, that persists even in the absence of particles. This concept fundamentally changes how we understand the universe's origins. Rather than starting from absolute emptiness, maybe the nothing of our universe is more like a quantum vacuum, an energetic, unstable playground capable of seeding new particles, and, ultimately, entire universes. One of the most striking consequences of quantum mechanics is the notion of quantum tunneling. That's when a particle can hop through an energy barrier that classical physics would forbid. Imagine a ball rolling uphill. It doesn't have enough energy to reach the top and roll down the other side. But in the quantum world, there's a finite probability that the ball can suddenly appear on the other side, as if by magic. These tunneling events aren't rare accidents. They're baked into the very fabric of quantum physics. This phenomenon hints that in a quantum vacuum, fields can spontaneously fluctuate, sometimes reaching threshold levels that lead to the creation of particles. This leads us directly into the idea of vacuum decay and the birth of particles. The quantum vacuum isn't static. It can undergo transformations. Sometimes, a fluctuation can be so significant that it triggers a transition to a different state. releasing energy that manifests as particles. This process can be seen in phenomena like Hawking radiation, where pairs of virtual particles near a black hole's event horizon become real, with one falling in and the other escaping as radiation. Does this mean that the universe itself could have emerged from these quantum fluctuations? Many cosmologists believe so. During the tiniest fractions of a second after the Big Bang, the universe undergoes a phase of rapid expansion called inflation. Quantum fluctuations during this period would have been stretched to macroscopic scales, seeding the entire cosmos with tiny variations in density. These variations eventually grew into galaxies, stars, and planets. Understanding nothing through quantum mechanics reveals that the very foundation of reality is less about a void and more about a dynamic, energetic field of probabilities. The vacuum isn't silent or empty. Instead, it's alive with potential, constantly bubbling with energy and uncertainty. This quantum dance hints that the origin of matter, the birth of atoms, and perhaps even our entire universe could have arisen from these ephemeral quantum jitters, an elegant reminder that even in emptiness, possibilities abound. The universe's story is like a vast cosmic puzzle, and one of the biggest pieces supporting the Big Bang theory comes from the observation of the universe's expansion. In the early 20th century, astronomers noticed something astonishing. Galaxies were not stationary islands in space. They were moving away from us, and the farther they were, the faster they seemed to recede. This relationship, now known as Hubble's law, showed the universe is stretching out over time. It's as if space itself is expanding, a clear sign everything started from an incredibly dense and hot state. Another key piece of evidence is the discovery of the cosmic microwave background, CMB radiation. In the late 1960s, scientists like Arno Penzias and Robert Wilson detected a faint uniform glow permeating the universe. It was as though the universe was basking in its own glow from an initial hot, dense state. This residual heat from the Big Bang has been stretched out over billions of years as the universe expanded and cooled. Its presence is like a snapshot from when the universe was only a few 100,000 years old, an afterglow of its fiery birth. Closely related is the observed abundance of light elements, such as hydrogen, helium, and traces of lithium. When the universe was a few minutes old, temperatures soared so high that nuclear reactions fused protons and neutrons, creating these elements in predictable ratios. When scientists compare these predicted abundances with observations, they match remarkably well. This alignment paints a vivid picture of a hot, dense, early universe, where conditions for primordial nucleosynthesis, the process that created these elements, were just right for the theories to hold true. Further supporting evidence comes from the universe's structure. The distribution of galaxies, galaxy clusters, and intergalactic gas follows patterns aligned with models of an expanding universe with a hot, dense origin. Simulations that start from initial conditions matching the Big Bang faithfully recreate the large-scale cosmic web seen today. This web is more than beautiful. It's a map shaped by billions of years of gravitational interactions beginning from nearly uniform, hot conditions. The phenomenon of cosmic redshift also bolsters the Big Bang idea. When observing distant galaxies, their light stretches toward the red end of the spectrum. The farther away they are, the faster they seem to recede, and their light is more redshifted. It's as if space itself carries these galaxies outward, like a balloon inflating. This pattern of redshift has been mapped meticulously, and aligns perfectly with the model of an expanding universe that originated from a single dense point. Recent measurements of the universe's expansion rate, called the Hubble constant, add further nuances. While debates and ongoing refinements exist, these measurements still strongly support a universe expanding from an initial hot, dense state. The consistency across different methods and observations acts like cross-verifying evidence, each piece supporting the overall picture. Moreover, astronomers peer back in time by observing distant cosmic objects. The farther we look, the further into the past we see. Galaxies billions of light years away are observed at different evolutionary stages, all consistent with a universe that began hot and dense, and has been evolving since. The timeline derived from these distant galaxies matches predictions made by the Big Bang model. Finally, subtle fluctuations in the CMB, the tiny temperature variations, are a cosmic fingerprint. These encode information about the initial conditions, how matter and energy were distributed immediately after the Big Bang. High-precision measurements, especially from the Planck satellite, have mapped these tiny variations with unprecedented accuracy, matching predictions of the Big Bang theory and inflationary models. All these pieces, universal expansion, cosmic microwave background, elemental abundances, cosmic structure, redshift patterns, and fluctuations, interlock into a grand narrative. They depict a universe that began from a hot, dense state roughly 14 billion years ago, expanding and cooling over time. This weight of evidence has transformed the Big Bang from a speculative idea into the leading scientific explanation for our universe's origins. Each discovery builds upon the last, revealing that everything we see, every galaxy, star, and atom, emerged from an explosive beginning from seemingly nothing but space-time itself. Imagine a universe that didn't just expand but did so at an incredibly rapid rate, stretching the fabric of space itself in an instant, like a balloon being blown up faster than you can blink. This phenomenon, known as cosmic inflation, was a fleeting yet profound moment in the universe's earliest fractions of a second. It might sound like science fiction, but it plays a crucial role in explaining how the universe came to be in its current state. Cosmic inflation was proposed in the early 1980s by physicist Alan Guth, motivated by puzzles left by the Big Bang theory. Before inflation, the prevailing view was that the universe began from an infinitely dense point, a singularity that then expanded. However, many details didn't quite fit this picture. How could distant parts of the universe appear so similar despite being out of each other's reach? Why is the universe so uniform and flat on large scales? These questions troubled cosmologists seeking explanations beyond the traditional Big Bang model. Inflation offers that explanation by proposing a brief epoch of exponential expansion, during which the universe grew by at least 10 to the 60th power, more than 100 billion times, in a tiny fraction of a second. This colossal stretch smoothed out irregularities and flattened the universe's curvature, resulting in the large-scale uniformity and flatness we observe today. It's akin to stretching a wrinkled cloth into a perfectly smooth sheet. Any initial wrinkles would be ironed out during inflation. But what triggered this sudden expansion? The key is a high-energy state associated with a field called the inflaton. Think of the inflaton as an energy reservoir filling space, dominating the universe's energy density during inflation. As the inflaton decayed or transitioned into more stable states, it released energy, causing the universe to rapidly expand. This rapid expansion stretched out any initial irregularities, setting the stage for the universe we see now. How does inflation relate to the universe's initial conditions? Before inflation, the universe could have been a tiny, hot, dense region with some randomness, like a chaotic boiling pot. Inflation acts as a cosmic reset button. It not only expands space dramatically, but also amplifies tiny quantum fluctuations, random variations in energy at the subatomic level. These microscopic ripples stretch to macroscopic scales during inflation, becoming the seeds for all cosmic structures, galaxies, stars, planets, and us. Imagine a tiny bump on a balloon surface that, as the balloon inflates, becomes a gentle hill. These bumps form the initial density differences across the universe. Slightly denser regions attract more matter, pulling in gas and dust over billions of years, leading to galaxy and cluster formation. Without inflation, these fluctuations would be too irregular or small, making the universe's large-scale uniformity and structure hard to explain. Inflation effectively set the initial conditions for the universe, creating a nearly uniform cosmic landscape. It also explains why the universe appears so flat, because the rapid expansion stretched any curvature until it became nearly indistinguishable. Think of rolling a small, uneven ball across a vast pancake. It appears flatter as the surface stretches. Similarly, inflation smooths out the universe's geometry. The story doesn't end there. The end of inflation was as crucial as its start. As the inflaton field decayed, it transferred its energy into particles and radiation, reheating the universe to high temperatures, like a cosmic furnace igniting. This process led to the hot Big Bang, where particles collided, combined, and formed atoms. In essence, cosmic inflation is a giant cosmic rollercoaster ride at the universe's dawn. It took the universe from a tiny, chaotic state into the vast, mostly uniform cosmos we see today. It set the initial conditions for structure formation, guided the distribution of energy and matter, and laid the blueprint for everything that followed. Without inflation, it's hard to see how the universe could have become so uniform, flat, and structured, giving rise to galaxies, stars, planets, and life. Cosmic inflation isn't just a runaway expansion. It's a fundamental process that prepared the universe's very fabric. It transformed an unimaginably small, chaotic beginning into a universe rich with potential for complexity, one capable of spawning galaxies, stars, and atoms. It created the conditions necessary for the universe's rich structure and diversity, explaining the uniformity, flatness, and large-scale organization observed today. Imagine the vast, silent void before everything we know. The space-time fabric stretched thin and empty, seemingly devoid of energy or matter. It's tempting to think of this emptiness as entirely nothing, but in the strange, counterintuitive world of quantum physics, even nothing isn't quite so empty. Instead, it's a frothing sea of potential, teeming with tiny, fleeting energy fluctuations that flicker in and out of existence, at scales so small they boggle the mind. This idea, that our universe might have emerged from a quantum fluctuation, has fascinated physicists for decades. The question is, could such a minuscule, spontaneous blip of energy have sparked the entire cosmos into being? At the heart of this hypothesis lies quantum mechanics, the science of the very smallest scales, where particles appear and vanish, and uncertainty reigns. In the quantum world, a vacuum isn't absolute nothing. It's a realm where particles and antiparticles momentarily pop into existence in pairs, then annihilate each other and disappear as quickly as they came. These fluctuations are intrinsic to quantum fields permeating all of space. In the early universe, a similar process might have occurred on an unimaginably grand scale. Instead of tiny particle pairs, imagine a fluctuation so significant it caused space itself to balloon outward, a process called cosmic inflation. This rapid stretching of space-time could have been triggered by a quantum fluctuation in a scalar field, an abstract energy field that fills the universe, similar to how electromagnetic fields fill space. Picture this. In a quantum vacuum, the energy level isn't always zero. Sometimes it takes on a tiny temporary spike, a fluctuation, that nudges the field out of its balanced state. If this fluctuation was large enough, it could have pushed the field into a different energy configuration, setting off a chain reaction that caused space to expand exponentially. This rapid expansion would dilute the energy density, smoothing out initial irregularities and setting the stage for the Big Bang. The intriguing part is that, according to some models, once such a fluctuation occurs, it can become self-sustaining and eternal in some regions, leading to a multiverse of bubble universes, each born from its own quantum spark. In this view, our universe is one such bubble, emerging from a seething quantum vacuum, a rare but inevitable fluctuation in an infinite sea of possibilities. But how does this quantum origin relate to the formation of atoms? It all ties back to the energy released during these fluctuations. The initial surge of energy from the quantum fluctuation set the universe in motion, fueling subsequent processes of particle creation and cooling. As the universe expanded and cooled, quarks combined into protons and neutrons, subatomic building blocks, and these formed nuclei during nucleosynthesis in the first minutes. Following this, as the universe continued cooling over hundreds of thousands of years, electrons found their way to orbit these nuclei, creating the first atoms, primarily hydrogen and helium. It's astonishing that these fundamental particles and simple atoms originated from the initial spark, a quantum fluctuation originating from nothing, or rather a quantum vacuum that teemed with potential. This hypothesis isn't merely speculative, it draws from laws governing quantum mechanics and cosmology. The mathematics describing these phenomena suggest fluctuations of energy are not only possible, but inevitable within quantum theory. The challenge lies in understanding how such a fluctuation could have grown from a tiny, probabilistic event into an entire universe of space, time, matter, and energy. Physicists continue exploring these ideas using models based on quantum field theory and general relativity. They grapple with the notion that the universe's birth wasn't caused by an outside force, but was a spontaneous event rooted in the fundamental properties of nature itself. It's a radical and humbling concept, that from fleeting, uncertain quantum foam, something as vast and ordered as our universe could arise. The notion that the universe originated from a quantum fluctuation offers a profound perspective. It implies that the fabric of reality is inherently unpredictable, and that the seeds of everything we see, from stars to simple atoms, may have been stitched into the universe's earliest moments, flickering into existence in a quantum flash. In this light, the universe's birth isn't just a grand, cosmic event, but also a testament to the strange, beautiful and mysterious dance of quantum fluctuations, a dance that might have played endlessly, repeatedly, in the seemingly empty void long before our universe began. Imagine the universe as a vast, shimmering fabric woven from the smallest threads imaginable. These threads aren't exactly threads in the traditional sense. They're quantum fields, fundamental entities that stretch across all of space and time. A quantum field is like an invisible, all-encompassing ocean that permeates the universe, continuously vibrating and fluctuating at every point in space. Unlike particles, which are often thought of as tiny, solid spheres zipping around, quantum fields behave more like dynamic, energetic landscapes. Think of a calm pond, perfectly still. If you drop a pebble, ripples spread out, creating waves that move across the surface. In the quantum world, these ripples are akin to particles appearing as a result of the vibrations of their respective quantum fields. So, rather than particles existing as tiny static objects, they are oscillations or localized excitations within their fields. To understand this better, picture quantum fields as the universe's underlying backdrop, an ever-present continuous field that exists everywhere. Every type of particle is associated with its own unique quantum field. For example, there's an electron field, a photon field, a quark field, and many more. These fields are never truly at rest. They're inherently active, constantly experiencing tiny, spontaneous fluctuations. These fluctuations are not random art. They are governed by the strange probabilistic rules of quantum mechanics. Now, how does a particle emerge from a field? When the field gains energy, say, through some ripple or disturbance, it can excite a specific localized vibration, a quantum of the field, which we perceive as a particle. It's like plucking a guitar string. Pluck it once, and a single wave or note is produced. If you pluck it repeatedly or with enough force, more complex vibrations emerge, corresponding to different particles or energy states. One way to visualize this is to imagine the entire universe filled with countless tiny invisible springs, each spring representing a quantum field. When you wiggle one of these springs just right, it creates a localized burst of vibration, a particle. But until that energy is given or the field is disturbed, no particle exists in that location. The particle is not a tiny static object hovering around. It's the fingerprint of the underlying quantum field's vibrations. This perspective marks a fundamental difference from the idea of particles as tiny billiard balls traveling through space. While classical particles have well-defined positions and speeds, quantum particles are more like ephemeral blips, probability clouds that only solidify into a defined location when measured or observed. Their existence is deeply tied to the state of their corresponding quantum field. Even more intriguing is that quantum fields are not just the source of particles, but they are also woven into the very fabric of reality. They provide a framework where particles can spontaneously appear and vanish, a process known as quantum fluctuation. These fluctuations can happen without any external cause, simply as a consequence of the intrinsic nature of the fields. In the moments after the Big Bang, these quantum fields played a crucial role. Tiny fluctuations in the energy of the quantum fields could have been magnified during inflation, creating regions of slightly higher or lower density. These tiny variations served as the seeds for the formation of galaxies and stars, illustrating how deeply interconnected quantum fields are with the structure of the universe itself. To sum it up, quantum fields are the fundamental entities that underpin all particles. Instead of viewing particles as little solid spheres, think of them as the localized spots of energy, where the ever-present quantum fields vibrate most intensely. These fields are the universe's subtle, all-encompassing fabric, with particles emerging as their discrete excitations. This perspective shifts our understanding from a universe made of tiny objects to one woven from the delicate, energetic waves of quantum fields, an elegant dance of energy and probability shaping everything we see and know. Imagine the fabric of reality as a vast, invisible ocean of energy known as quantum fields, stretching across the entire universe. These fields never truly rest. They're constantly flickering with activity, and it is within this restless sea that virtual particles come into existence. But how do these ephemeral entities emerge from something that's, by all accounts, supposed to be empty? In the quantum world, fields are the fundamental entities underlying everything we see and do not see. Each type of particle, electrons, photons, quarks, corresponds to a specific quantum field. Even in what seems like a perfect vacuum, these fields are not silent. Instead, they are in a state of ceaseless fluctuation. These fluctuations are not random noise, but are governed by the strange and fascinating laws of quantum mechanics, which tell us that energy can temporarily appear to be borrowed from the vacuum, provided it is returned in a very short amount of time. This borrowing operates under the strict conditions of the Heisenberg uncertainty principle. Essentially, the principle sets a limit on how precisely we can know both the energy and the time involved in a process. As a result, the vacuum becomes a bubbling, roiling expanse, where pairs of virtual particles flicker into existence for infinitesimally brief moments, before annihilating each other and vanishing once again. These pairs are often referred to as virtual, because they are not directly observable in the same way as real, detectable particles. They are, however, real in their effects, influencing phenomena such as the Casimir effect, which demonstrates how quantum fluctuations can generate measurable forces between objects. These virtual particles are not like the particles you find in a laboratory, zipping around at high speeds, because they cannot be detected directly. Instead, their presence is inferred from these subtle effects. They are mathematical manifestations of the underlying quantum fields. Whenever a real particle appears or interacts, it often does so through the fleeting existence of these virtual particles. For example, in particle collisions at the Large Hadron Collider, the exchange of virtual particles mediates the fundamental forces, like the electromagnetic force carried by virtual photons, or the strong force mediated by virtual gluons. Despite their ephemeral nature, virtual particles play an outsized role in shaping the universe. They contribute to the energy of the quantum vacuum, which in turn influences the evolution of the cosmos itself. The vacuum isn't simply nothing, but a frothing quantum sea, filled with constant spontaneous activity. Sometimes, these virtual particles manage to gain just enough energy to become real, a process that might have seeded the initial structures of the universe itself. From the seemingly empty depths of space, then, The emergence of virtual particles illustrates a universe that is never truly silent or void. Instead, it is alive with quantum fluctuations, a restless dance of energy and creation that underpins everything, from the smallest subatomic particles to the grand architecture of galaxies. Imagine the fabric of the quantum vacuum, seemingly empty yet teeming with activity at the smallest scales. In this realm, particles and their mirror images, antiparticles, can spontaneously appear and vanish almost instantly. This phenomenon, known as particle-antiparticle pair creation, is fundamental to understanding how matter might have arisen from nothing. At its core, pair creation occurs due to the strange laws of quantum mechanics. Unlike everyday experiences, where something can't come from nothing without external energy or force, the quantum world operates on probabilities and fluctuations. The vacuum isn't truly empty, but a restless sea of energy, constantly fluctuating with tiny virtual particles blinking in and out of existence. These virtual particles are too fleeting to observe directly, but are essential to the universe's quantum structure. Under certain conditions, especially when energy is supplied, these virtual particles can become real, detectable particles that persist longer than a brief moment. This transition hinges on Einstein's famous E(I)mc2 equation, which states energy and mass are interchangeable. If enough energy is localized in a region of space, it can manifest as a particle-antiparticle pair. Think of energy as a seed, powerful enough to generate matter from quantum potentiality. One key scenario for pair creation is near an extremely intense electric field. Imagine a region with such a strong electric field that it distorts the vacuum's quantum fluctuations, effectively ripping virtual pairs apart and turning them into real particles. This process was theorized by Julian Schwinger and is called the Schwinger effect. It vividly illustrates how energy input can give rise to particles from empty space. The intense energy acts as a catalyst, pushing virtual pairs over the threshold into reality, much like a spark igniting a fire. Another fascinating process involves a strong gravitational field, such as near a black hole's event horizon. When virtual pairs form close to the horizon, gravity can pull one particle inward while allowing the other to escape. This phenomenon is Hawking radiation. It causes black holes to emit particles and gradually lose mass. The curved space-time provides the energy needed for particle creation, demonstrating how gravity itself can turn nothing into something. Regarding the universe's earliest moments, just fractions of a second after the Big Bang, the energy densities were unimaginably high, creating a cosmic storm for pair production. The universe was a hot, dense plasma where particle-antiparticle pairs formed and annihilated rapidly. As expansion cooled the cosmos, some particles remained, forming the building blocks of matter that eventually led to stars, planets, and life. It's crucial to recognize that pair creation isn't rare but a fundamental aspect of quantum field theory, the framework describing all known particles and forces. The vacuum's energy fluctuations constantly generate virtual pairs, subtly influencing fields and particles always. Under natural conditions, these virtual pairs are ephemeral, annihilating into energy almost instantly. However, when external energy, such as from intense electromagnetic or gravitational fields, becomes available, these pairs can transition from virtual to real, persistent particles. This process underscores a profound truth. Nothing in the quantum universe is truly static or empty. Instead, nothing is a dynamic state filled with potential. Energy fluctuations, quantum tunneling, and pair creation weave together, transforming the quantum vacuum into the seedbed of all matter. When the universe emerged, quantum fluctuations likely sparked the initial particles that formed atoms and galaxies. Particle-antiparticle pair creation isn't just a quantum curiosity, it's a fundamental mechanism connecting energy, space-time, and matter. It reveals that from the trembling uncertainties of the quantum vacuum, the universe could have come into existence, turning nothing into everything we observe today. Exploring these processes peels back deeper layers of the cosmic story, a narrative where the fabric of reality begins with spontaneous quantum dances, beautiful, fleeting, and endlessly fascinating. Imagine the universe in its earliest moments, a seething, frothing quantum landscape where the very fabric of space is alive with activity. In this primordial sea, space isn't calm or static. Instead, it's filled with ceaseless energy fluctuations, tiny ripples that flicker in and out of existence in an unpredictable dance. These are quantum fluctuations, a fundamental aspect of the quantum world where uncertainty becomes the rule rather than the exception. In classical physics, empty space might seem truly empty, a void devoid of anything. But quantum mechanics shows us a more complex picture. The vacuum isn't just emptiness, it's a frothy, restless soup of energy, constantly bubbling with ephemeral particles popping in and out of existence. Think of it like a boiling pot of water, only here, The bubbles are tiny, momentary disturbances in the energy field, lasting just for a fleeting instant before vanishing again. These spontaneous fluctuations are governed by the uncertainty principle, which tells us we can't precisely know both the energy and the time simultaneously. This inherent unpredictability means energy can appear and disappear with a kind of quantum grace. Now, how does this jittery quantum activity give rise to actual particles? It hinges on quantum tunneling and the energetics of the vacuum. Usually, particles like electrons or quarks need some energetic push to come into existence. In the early universe, the energy within the fluctuating vacuum was colossal, far beyond what modern labs can generate. These enormous energy fluctuations occasionally reached a threshold where particle-antiparticle pairs could spontaneously form from the seething energy. Picture these fluctuations as tiny sparks flung off by the energetic chaos. Sometimes, a spark becomes a sustained flame, transforming into a real particle if it taps into enough energy momentarily. According to Einstein's famous equation, E equals mc squared, energy and mass are interchangeable. So if a fluctuation provides enough energy, it can give birth to a particle with mass. For example, an electron and its antimatter counterpart, the positron, can emerge from this energy burst, only to annihilate each other if they meet again, cancelling out into pure energy once more. In the early universe's extraordinary conditions, the story extends further. The rapid expansion, cosmic inflation, stretched space itself, causing fluctuations to become larger and more pronounced. As space expanded exponentially in a tiny fraction of a second, quantum fluctuations were magnified, frozen into the fabric of space-time. These amplified fluctuations seeded the formation of large-scale structure, galaxies, clusters, and cosmic webs. The process is akin to ripples on a pond caused by a thrown stone. The initial stone creates small ripples, but if the pond is churning or external forces magnify these ripples, they can grow into massive waves. In the universe's infancy, quantum fluctuations served as the tiny seeds that, through inflation, grew into the structures we observe today. These fluctuations didn't just produce particles, they set the stage for the universe's architecture. Regions with slightly higher energy densities, born from these fluctuations, started to gravitationally attract matter, pulling in more particles and forming the first galaxies. Over billions of years, this process led to the complex structured universe we see today. While the precise mechanisms remain under study, it's astonishing how quantum jitters in nothingness could blossom into particles and structures. Quantum fluctuations act as a grand cosmic symphony, and spontaneous dance of energy and uncertainty that ignited matter's birth. From the chaotic quantum froth, particles emerged in a miraculous, fleeting, and ultimately inevitable process. These particles eventually collided, combined, and evolved, forging the universe's fabric. Quantum fluctuations weren't just random noise, they were the initial spark in a vast cosmic story, a whisper in the dark that grew into the universe. This process explains how the tiniest quantum shifts led to the creation of matter and structure, setting the stage for everything we see today. The universe's beginning, shaped by these fleeting quantum disturbances, exemplifies how the fundamental rules of quantum mechanics can produce the grand universe from seemingly nothing, marking the birth of everything in a spontaneous, intricate dance of energy, uncertainty, and cosmic potential. The universe's earliest moments feature a crucial but often overlooked element, the Higgs field, essential for understanding how particles gain mass. Imagine the universe as a bubbling energy cauldron, where particles are born seconds after the Big Bang. Initially, these particles were massless, whizzing through space at the speed of light, unable to form the structures we observe today. Without the Higgs field, particles would remain massless and unable to coalesce into matter. So, what is the Higgs field? Think of it as an all-pervasive, invisible energy filling space, a cosmic molasses that particles pass through. When the universe was extremely hot and dense, particles emerged as pure energy, oscillating in complex patterns. During this early chaos, their interactions with the Higgs field began to shape their destiny. Particles that interact strongly with the field experience resistance, which manifests as mass. The more they interact, the heavier they become. Particles like photons, which barely interact, stay massless and travel at light speed. This interaction explains why particles have different masses, a foundation of matter's structure. The origin of the Higgs field itself remains a deep mystery at the intersection of particle physics and cosmology. The 2012 discovery of the Higgs boson at CERN confirmed the field's existence. The Higgs boson can be viewed as a ripple, a wave, in this vast energy field, offering clues about its nature. In the universe's earliest moments, temperatures were so high that the Higgs field didn't have a stable value. Particles existed as massless entities zipping through space at light speed. As the universe expanded and cooled, the Higgs field settled into a non-zero value, a phase transition comparable to water freezing into ice. This pivotal moment allowed particles to acquire mass, enabling the formation of protons, neutrons, and electrons. Once particles gained mass, they could bind together, forming atoms, the fundamental unit of matter. Without the Higgs field's influence, particles would be massless, making atomic and molecular formation impossible. Mass provided the weight necessary for particles to slow down, interact, and stick together under gravity. This interplay led to the creation of stars, planets, and galaxies, shaping the observable universe. The Higgs field's role extends beyond individual particles. It influences matter clustering, galaxy formation, and the universe's evolution. Without it, matter's properties would be so different that the universe might lack the structure and stability necessary for life. The Higgs field also intersects with the concept of vacuum energy rooted in quantum field theory. Even in its lowest energy state, the Higgs field maintains a non-zero value, meaning space isn't truly empty, but filled with a subtle energy influencing the cosmos's expansion. This quantum vacuum contains energy fluctuations capable of affecting particle creation and the universe's overall development. It highlights that what appears to be empty space is a dynamic, energetic fabric, not nothing. Visualize the importance of the Higgs field like walking across a room filled with sticky syrup. Without the syrup, movement is swift and easy. With it, progress slows, and you stick depending on the syrup's thickness. Similarly, the Higgs field gives particles their mass, controlling their movement and shaping cosmic evolution. Particles with more interaction become heavier, influencing how structures form and how the universe changes over time. The Higgs field functions as both a sculptor and a cornerstone of the universe. It transformed an energy ocean into a cosmos filled with particles of varying masses, enabling the grand dance of matter, energy, and forces. Without this invisible field, atoms, molecules, stars, and even life would never materialize. It's a reminder that what appears empty is filled with profound energy and subtle forces, quietly orchestrating the universe's journey from nothing to everything. The Higgs field, thus, remains fundamental for understanding our existence and the universe's complex beauty. Einstein's equation, EMS2, explains how energy transforms into matter. It states that energy and mass are interchangeable under specific conditions. How does this work in a universe where atoms seem to come from nothing? Immediately after the Big Bang, energies and temperatures were unimaginably high. Particles were created naturally and continuously. Space was filled with a quantum field of virtual particles flickering in and out of existence, constantly borrowing and returning energy as per quantum mechanics. In this energetic quantum soup, a surge of energy can spontaneously produce particles. Conservation of energy still holds, but within quantum fields, particles appear as virtual entities popping in and out of existence. How do these virtual particles become real matter? The key lies in Einstein's equation, linking energy and mass. Particles can emerge from pure energy when conditions are just right. Specifically, when enough energy is concentrated in a tiny space. According to Einstein, this energy converts into mass, creating particles like electrons and quarks from energy alone. These virtual particles become real when energy surpasses a certain threshold. During the early universe's rapid inflation, immense energy densities made virtual particles stable enough to become actual particles. It's like a spark igniting a fire. The extreme conditions supply enough energy for virtual particles to gain real mass. Particles can also annihilate back into energy, maintaining a balance governed by physical laws. Einstein's equation clarifies that the energy needed to produce a particle is proportional to its mass times the speed of light squared. Since c is enormous, even tiny amounts of energy can generate significant mass. This principle allows high-energy photons, light packets, to create particles when they collide or interact within the quantum vacuum. When two high-energy photons meet with enough combined energy, they can produce a particle-antiparticle pair such as an electron and a positron. This pair production exemplifies Einstein's insight. The energy in photons effectively acts as mass, materializing as particles. The energy-to-matter transformation is continuous and reversible, a balanced dance of the universe. This process isn't limited to the early cosmos. Today, scientists in particle accelerators collide particles at near-light speeds, observing energy's direct conversion into new particles. Why is this energy-to-matter conversion fundamental to atomic formation? Particles created from high-energy conditions are the building blocks of matter. Once particles like protons, neutrons, and electrons come into existence, they combine into atoms, the building blocks of stars, planets, and all observable matter. This energy-matter interchange highlights the universe's deep interconnectedness. All matter, from galaxies to molecules, originated from energetic conversions, from the universe's earliest moments to now. This cosmic dance is choreographed by fundamental physics laws, where energy and matter are different expressions of the same reality. Einstein's EM2 isn't just theoretical, It's a blueprint for how the universe was built from energy. Every atom we see was once just a burst of energy, transformed into matter by physical laws. The equation reveals that, in the quantum cosmos, nothing truly comes from nothing. Instead, everything emerges from energy converting into matter, governed by core physical laws. The universe's creation story is rooted in this energy-matter interchange. From the Big Bang to today's structures, this transformation underlies all physical existence. High-energy photons and quantum fluctuations continually produce particles when conditions allow, illustrating the elegance of physical law. The conversion from energy to matter is a fundamental, ongoing process, a balanced, reversible dance that forms everything we observe. It makes clear that matter is merely energy in another form, shaped by the universe's rules, blending energy and matter into a unified whole. Every particle of matter in the universe originated from energy. This insight is captured by Einstein's equation. This fundamental link, energy transforming into matter, defines the fabric of reality. It's a cosmic cycle beginning with the Big Bang and lasting today. High-energy phenomena generate atoms and molecules that make up galaxies, stars, planets, and ourselves. This interconnection underscores the universe's unity and the power of its governing principles. In the quantum universe, mass and energy are two sides of the same coin. Matter and energy continually exchange and transform, exemplifying the harmony of physical laws. Einstein's E-mc2 remains central, revealing that the universe's fabric is woven from energy, manifesting as matter through these fundamental laws. In the first moments after the Big Bang, the universe was an unimaginably hot, dense sea of energy. Temperatures soared to trillions of degrees, and particles like quarks and gluons moved at incredible speeds. Under these conditions, atoms or familiar matter couldn't exist. Instead, everything was in a state of plasma, energetic, free-moving particles that collided constantly. As the universe expanded, it cooled. This rapid cooling was essential. It created conditions where particles could transition from high-energy, free states to more stable configurations. Imagine a furnace gradually turning down its heat, allowing raw energy to settle into more ordered forms. Within a few 100,000 years, the universe's temperature dropped to about 10,000 Kelvin. Still extremely hot by earthly standards, this cooling allowed the energetic chaos to settle. Electrons, which had been bouncing at relativistic speeds, began interacting more with protons and neutrons, the building blocks of atomic nuclei. For atoms to form, free electrons needed to bind with nuclei without being knocked away by radiation. Early universe conditions were filled with high-energy photons, packets of light, that constantly bombarded charged particles, preventing stable unions. This made the universe opaque. Light couldn't travel freely because it was scattered by free electrons, a process called Thomson scattering. But as the universe cooled further, photon energies decreased. Eventually, they lacked enough power to eject electrons from protons or neutrons. This epoch, known as recombination, happened roughly 300,000 years after the Big Bang. During this time, electrons paired with nuclei to create neutral atoms, mainly hydrogen and helium, the simplest and most abundant elements. When electrons combined with protons to form neutral hydrogen, radiation decoupled from matter and light began to travel freely. This event marked the origin of the cosmic microwave background radiation, a faint glow left over from this era, giving us a snapshot of the early universe. The formation of neutral atoms was only the start. The universe continued to expand and cool, allowing these atoms to clump together under gravity. Tiny density variations, seeded by quantum fluctuations in the early universe, created initial lumps of matter. Over time, these density fluctuations grew, pulling in more matter and forming larger structures like gas clouds. These clouds eventually condensed under gravity, leading to star formation. The universe's conditions for atom formation depended on a delicate balance. It had to cool enough for charged particles to stick together, but not so quickly that matter couldn't stay neutral. The balance of radiation, temperature, and density created a fleeting window, when atoms could finally form from the primordial chaos. Once formed, these atoms became the building blocks for subsequent cosmic evolution. Hydrogen, with just one proton and one electron, served as the universe's fundamental ingredient. Over billions of years, hydrogen gathered into vast clouds, experiencing turbulence, shocks, and gravity, eventually igniting into stars. Inside stars, nuclear fusion transformed hydrogen into heavier elements like carbon, oxygen, and iron, elements that would later be scattered across the cosmos, forming planets, atmospheres, and life. The conditions that allowed atom formation were characterized by a series of extraordinary changes. Initially, a universe so hot that particles existed in a free energetic state. Then, as it expanded, cooling sufficiently for particles to bind into neutral atoms. When the high-energy photons receded enough, electrons could settle into stable orbits around nuclei. This marked the dawn of matter, a transition from raw energy to structured universe. This remarkable process was driven by the interplay of physics, quantum mechanics, thermodynamics, and gravity, working together to shape the cosmos from mere energy. The balance of these forces during the early universe created the conditions for atoms to emerge from chaos, laying the foundation for everything we see today. As we explore the origins of matter, it's fascinating to see how the smallest building blocks, quarks, came together to form protons and neutrons which make up atomic nuclei. These particles are key pieces in understanding how the universe evolved from a mysterious nothing into the complex matter we observe today. In the earliest moments after the Big Bang, the universe was a hot, dense energy soup, an environment so energetic that particles were constantly created and destroyed in chaos. During this epoch, quarks and gluons, the carriers of the strong force, existed freely, roaming in what physicists call a quark-gluon plasma. The temperature was so high that quarks couldn't yet form stable particles. Instead, they floated in a sea, exchanging energy and interacting continuously. As the universe expanded and cooled within the first few microseconds, conditions changed dramatically. When temperatures fell below a critical threshold, about 2 trillion degrees Celsius, quarks began to combine into more complex structures. This process was driven by the strong nuclear force, a fundamental interaction vastly stronger than the electromagnetism at small scales. It's this force that holds atomic nuclei together and binds quarks into protons and neutrons, shaping matter itself. Quarks, although minuscule, roughly 1/100th of a trillionth of a centimetre, cannot exist in isolation under normal conditions. They are confined within larger particles called hadrons, a phenomenon known as colour confinement. Imagine an unbreakable glue holding these quarks together. This is the strong nuclear force at work. It's incredibly intense, increasing as quarks drift apart, ensuring they stay bound once formed as protons or neutrons. Protons consist of 2 up quarks and 1 down quark, while neutrons are composed of 2 down quarks and 1 up quark. The up quark carries a charge of plus 2/3 the elementary charge. The down quark has a charge of minus 1/3. When combined, these charges give the particle its overall electric charge. 2 up quarks plus 1 down quark in a proton sum to a positive charge, making it positively charged. Conversely, 2 down quarks plus 1 up quark in a neutron cancel out the positive charge, resulting in a neutral particle. But how do these quarks know to stick together in this specific configuration? It's governed by quantum mechanics and the principles of quantum chromodynamics, QCD, which describe how quarks behave and interact via the strong force. When quarks come close, the strong force effectively pulls them into a bound state. This process is like a cosmic dance where quarks pair, fuse and stabilize into particles that form matter. This binding wasn't simple. It involved complex interactions mediated by gluons, the particles transmitting the strong force. Gluons act as messengers, constantly exchanging colour charge, a property similar to electric charge but specific to the strong force, among quarks. The result is a tightly bound trio forming either a proton or a neutron, depending on their specific combination. Beyond their individual characteristics, protons and neutrons are called baryons, particles made of 3 quarks. The stability of these baryons varied in the early universe. Some neutrons were unstable, decaying into protons, electrons and antineutrinos if not quickly captured into nuclei. However, enough neutrons survived long enough to participate in forming nuclei during later cosmic stages. Once protons and neutrons could combine into the simplest nuclei, like deuterium, which has 1 proton and 1 neutron, the stage was set for nuclear fusion in stars. These processes build heavier elements, but their origins trace back to the primordial quark combinations in the universe's earliest moments. The story of how quarks combined into protons and neutrons isn't just about particles sticking together. It's about the fundamental forces and quantum principles that govern matter at tiny scales. It's a cascade from initial energy chaos to particles that assembled into atoms, planets, and life. The universe's journey from nothing to everything hinges on these tiny but powerful quarks, weaving a cosmic story still being unraveled through physics research and the fabric of reality. Imagine the universe in its earliest moments, an incredibly hot, dense ocean of energy, swirling and shimmering with potential. As this primordial fireball expanded and cooled, it set the stage for the very formation of matter itself. This process, known as nucleosynthesis, is essentially the universe's way of forging its first building blocks, atoms, out of the simplest, most fundamental particles. Nucleosynthesis is the process by which atomic nuclei are formed. Right after the Big Bang, conditions were extreme. Temperatures soared into the billions of degrees, and particles like protons and neutrons were racing at astonishing speeds. Under these conditions, protons and neutrons, which are the core constituents of atomic nuclei, constantly collided and interacted. To understand how the first elements emerged, we need to explore what was happening during this cosmological event. Initially, the universe was filled predominantly with quarks and gluons, more fundamental than protons or neutrons. As the universe expanded and cooled to about 1 trillion degrees, quarks began to combine, sticking together through the strong nuclear force, giving rise to protons and neutrons. This transition marked the beginning of the formation of matter as we know it. Once protons and neutrons appeared, they started to interact more directly. When the universe cooled below about 1 billion degrees, roughly 3 minutes after the Big Bang, conditions became suitable for nuclear reactions. This is when nucleosynthesis truly began. This era, called Big Bang nucleosynthesis, lasted just a few minutes but was immensely important. During this time, protons and neutrons collided, fused, and rearranged to form the universe's first atomic nuclei. The earliest nuclei to form were the simplest: hydrogen nuclei, which are just protons, and helium nuclei composed of 2 protons and 2 neutrons. These reactions happened rapidly. For instance, a proton could fuse with another proton to produce deuterium, an isotope of hydrogen, via a process involving the weak nuclear force. If conditions allowed, that deuterium could then fuse with another proton to create helium-3, a lighter isotope of helium, or directly fuse to produce helium-4, the most stable helium nucleus. Because the universe was so hot, most newly born nuclei couldn't capture electrons immediately. The energy was too intense. Only as cooling progressed did the first atoms form, with electrons combining with nuclei, creating neutral hydrogen and helium atoms. This marked a turning point. The universe now contained its first stuff, the basic elements, poised to later coalesce into stars and galaxies. Nucleosynthesis didn't merely produce hydrogen and helium. Tiny traces of lithium and beryllium were also created. However, these elements existed in such small amounts, they weren't major players in early chemistry. Hydrogen and helium dominate most of the universe's matter even today, forming the bulk of the observable universe's composition. The significance of nucleosynthesis lies in its link between the universe's hot, chaotic beginnings and the complex chemistry observed today. It set the initial elemental makeup, providing ingredients for stars and planets to form later. Inside stars, nuclear fusion continued to create heavier elements: carbon, oxygen, nitrogen, iron, and beyond. All these elements trace their origins back to the first nucleosynthesis events. In a sense, nucleosynthesis is like a cosmic recipe, set in the furnace of the early universe. It's driven by fundamental forces: gravity, the strong nuclear force, and the weak nuclear force, and governed by quantum mechanics and thermodynamics. Those early moments, lasting mere minutes, were crucial in shaping the universe's chemical identity. Without nucleosynthesis, the universe would be just a uniform expanse of radiation and dark matter, a silent, empty void. Instead, it became filled with the ingredients for planets, life, and everything we observe. Every atom of hydrogen in our bodies, every oxygen molecule in the air, traces back to the moment when the universe cooled enough for nuclei to assemble. The story of nucleosynthesis is essentially how the universe took its first steps from a swirling sea of energy into a universe filled with matter, an incredible process transforming the energy of the Big Bang into atoms. These atoms over millions of years led to stars, galaxies, and ultimately us. Helium was among the first elements formed after the Big Bang because of the unique conditions that existed in the moments immediately following the birth of the universe. When the universe was just a few minutes old, it was incredibly hot and dense, so much so that atomic nuclei couldn't hold together. Instead, it was a seething, energetic soup of fundamental particles: protons, neutrons, electrons, and photons, constantly colliding and interacting in a rapidly expanding space. As the universe expanded, it cooled down. This cooling was essential because certain nuclear processes could only occur once the temperature dropped below specific thresholds. In the very early seconds, protons and neutrons were constantly transforming from one into the other via nuclear reactions, but they couldn't form stable nuclei just yet, due to the extreme energy environment. It was only after about 3 minutes that the temperature fell enough for protons and neutrons to combine, forming the first nuclei through a process called nucleosynthesis. During this nucleosynthesis phase, the universe was still incredibly hot, but it was cool enough for nuclear reactions to happen at a significant rate. The process favoured the formation of the lightest nuclei, primarily hydrogen and helium. Hydrogen nuclei are just single protons, and because they are the simplest and most stable, they formed rapidly. Helium nuclei, on the other hand, consist of 2 protons and 2 neutrons, creating a very stable configuration. Why specifically helium? It all comes down to nuclear stability and binding energy. The universe's initial conditions meant that as protons and neutrons collided, certain combinations were more likely to stick together. Helium's nucleus, with its 2 protons and 2 neutrons, is exceptionally stable, meaning it's less likely to break apart once formed. This stability led to it being the most common form of heavy element to emerge during this early period, surpassing all other possible combinations that could have been formed. The process didn't stop at just helium. There was enough time and the proper conditions for some traces of deuterium, heavy hydrogen, lithium, and tiny amounts of other light nuclei to form. But helium became the dominant heavy element in the early universe because of its stability and abundance. Once the universe cooled further, nuclear reactions slowed down considerably, and no new nuclei could form efficiently. The existing nuclei, mainly hydrogen and helium, then entered a long phase of cosmic expansion, floating through space as the building blocks for future stars and galaxies. This primordial mix of hydrogen and helium set the stage for everything that comes after: stars, planets, and even life itself. The fact that helium was so prevalent right after the Big Bang isn't just a quirk of cosmic history. It is a fingerprint written into the universe, revealing that these primordial nuclear processes took place under remarkably specific conditions and shaped the cosmic landscape for billions of years to come. As the universe expanded, it cooled. Immediately after the Big Bang, it was unimaginably hot and dense, so hot that protons, neutrons, and electrons couldn't form stable structures. Particles moved at incredible speeds, constantly colliding, being torn apart. It was a chaotic, high-energy environment with matter in relentless turmoil. As space expanded, the universe's temperature dropped. Think of inflating a balloon. As it expands, surface regions stretch apart. Similarly, expanding space causes particles to move farther apart and lose energy. Initially, the universe's temperature was trillions of degrees, preventing protons and neutrons from binding into stable nuclei. Any nuclei that formed were immediately broken apart by energetic photons zipping around at near-light speeds. So, for a time, the universe was filled with a hot plasma, a fiery soup of free protons, neutrons, electrons, and high-energy radiation, where matter and radiation behaved as one. The critical turning point occurred when the universe cooled beneath about a few billion Kelvin. Once below this temperature, photons lacked enough energy to break apart protons and neutrons easily, creating conditions for nuclear binding. This process, called nucleosynthesis, marked the formation of the first atomic nuclei. Protons and neutrons fused into simple nuclei, mainly deuterium, a proton and a neutron, which further fused into helium nuclei and traces of lithium. This happened within minutes after the Big Bang, forming the universe's first building blocks, primordial elements that laid the foundation for all matter. However, forming nuclei wasn't the end. These nuclei needed electrons to become neutral atoms. But the universe was still flooded with energetic photons, about 1,000 photons per nucleus, constant enough to knock electrons away. This electron kicking made it difficult for electrons to attach to nuclei, like trying to build something in a storm of wind. The breakthrough happened later when the universe cooled further, down to about 300,000 Kelvin, roughly 300,000 years after the Big Bang. At this point, photon energies diminished enough for electrons to recombine with nuclei, forming neutral atoms without being ripped away. This epoch, called recombination, marked a key transition. Electrons settled into orbitals around nuclei, creating neutral atoms. Before this, the universe was opaque and glowing brightly. The dense plasma scattered photons, preventing light from travelling freely. But once neutral atoms formed, photons could escape unimpeded, making the universe transparent. Today, this event is observed as the cosmic microwave background radiation, a faint glow detectable from all directions. The universe's cooling, driven mainly by expansion, caused particle energies to drop. As space grew, protons and neutrons could bind into nuclei, then later, electrons could attach to form atoms. This transition from hot plasma to neutral matter set the stage for galaxy formation, star birth, and planetary systems. Without this cooling, matter couldn't organize into complex structures. In essence, the universe's expansion led to decreasing temperature and particle energy, enabling nuclear fusion and then atomic formation. Nucleosynthesis produced the first elements, fuel for stars and galaxies. Recombination allowed light to travel freely, producing the cosmic microwave background and making the universe transparent. This sequential cooling process laid the groundwork for all cosmic structures. The transition from a dense, hot initial state to a cooler, transparent universe was vital for cosmic evolution. It allowed matter to clump under gravity, forming stars, galaxies, and planets, environments needed for life. Without this cooling, matter would have remained a hot, diffuse plasma, preventing the universe's complexity. Cooling just enough, the universe transitioned smoothly from chaos to structure. Cooling, driven by expansion, enabled the universe to evolve from a seething cosmic soup to a structured cosmos. The formation of stable atoms was essential, providing ingredients for everything known today. It was a gradual but profound process that allowed matter to settle into stable configurations. This paved the way for cosmic structures, from particles to galaxy clusters. The universe's ability to cool just enough was fundamental to its diversity and complexity. In conclusion, the universe cooled as it expanded, allowing protons and neutrons to form nuclei, then electrons to create neutral atoms, transitioning from opaque plasma to transparent space. This process laid the groundwork for stars, galaxies, and life. The universe's expansion and cooling are cornerstones of cosmic history, transforming initial chaos into the structured cosmos we see today. This delicate balance of processes made the universe hospitable, capable of supporting complex structures and life. Word count 613. Primordial nucleosynthesis, also known as Big Bang nucleosynthesis, is a key chapter in the universe's earliest moments. It is the process through which the universe formed its first simple elements, mainly hydrogen, helium, and traces of light nuclei, within the first few minutes after the Big Bang. Think of it as nature's first cooking attempt, where extreme heat, density, and rapid expansion created the right conditions for nuclei to form from a hot soup of fundamental particles. Right after the Big Bang, as the universe expanded and cooled from its unimaginably hot and dense state, protons and neutrons, the building blocks of atomic nuclei, began to collide and stick together. Early on, the universe was so hot that these nuclei once formed couldn't hold electrons to become stable atoms. Instead, they remained as free nuclei in a plasma so energetic electrons couldn't settle into orbits. It wasn't until about 3 minutes after the Big Bang, when the universe cooled enough, that protons and neutrons combined into nuclei without being immediately torn apart by the intense energy. During this brief period, most protons paired with neutrons to produce hydrogen nuclei. Including deuterium, neutrons bound to protons. Some neutrons fused with protons to form helium-4, a nucleus containing 2 protons and 2 neutrons, which is remarkably stable. There were very small traces of heavier light elements like lithium and beryllium, but their abundance was so low they played minor roles in cosmic chemistry. Primordial nucleosynthesis's significance lies not only in creating the universe's first elements, but also in establishing the initial chemical blueprint necessary for star, planet, and eventually life formation. These early elements served as raw materials for subsequent cosmic structures. Without the abundance of hydrogen and helium, the universe wouldn't display the rich diversity of galaxies, stars, and planets observed today. From a scientific detective's perspective, this process has been confirmed through observations of the cosmic microwave background and measurements of light elements in ancient gas clouds, which align precisely with Big Bang nucleosynthesis models. This agreement supports the idea that the universe started in a hot, dense state and expanded rapidly, enabling nuclear reactions to occur as physics predicted. It acts as a critical test confirming our understanding of how the universe evolved immediately after its inception. The proportions of the primordial elements also serve as clues to the universe's early conditions, such as the baryonic matter density, the amount of regular proton and neutron-based matter at that time. For instance, the observed helium abundance informs us about the nuclear processes that took place and the overall density of ordinary matter, independent of dark matter or dark energy. This makes primordial nucleosynthesis a cosmic fingerprint, offering insights into the fundamental composition and history of the cosmos. Understanding this process also connects the physics of the early universe with the later star and galaxy formation. The light elements produced in the first minutes became the fuel for the first stars that fused these elements into heavier ones. Over cosmic time, these stars and supernovae enriched the universe with heavier elements, leading to the formation of planets, oceans, and life itself. Moreover, the process illustrates how initial conditions, temperature, density, and expansion rate, govern the kinds and quantities of elements produced. This deepens our understanding of the universe's origin and guides investigations into physics beyond the standard model, such as dark matter and new particles. Slight deviations in predicted element abundances could signal physics beyond current theories, sparking new questions and exploration. In essence, primordial nucleosynthesis is both a cosmic clock and a chemical map. It reveals what the universe was like moments after its birth and influences its present structure. From tiny nuclei to vast galaxies, the story of how the simplest elements first formed echoes through space and time, reminding us that in those first minutes, the universe embarked on a transformative journey, one ultimately leading to our existence. The ratio of hydrogen to helium in the universe acts as a cosmic blueprint, revealing details about the earliest moments after the Big Bang. Measuring these proportions, the amounts of dark, light, and simple elements, allows scientists to peer back in time and understand the conditions during those first few minutes of existence. Immediately after the universe's birth, it was a hot, dense energy field. Temperatures soared, particles moved at incredible speeds, and the fundamental forces of nature were locked in a fiery contest. As the universe expanded and cooled faster than we can recreate, conditions eventually stabilized enough for atomic nuclei to form. This epoch, known as primordial nucleosynthesis, lasted only a few minutes but laid the groundwork for cosmic evolution. During this brief period, protons and neutrons fused into light elements. Hydrogen, with its single proton, was the most abundant, glowing quietly in the cosmic sea. Helium, with 2 protons and neutrons, was also produced in significant amounts. Trace elements like deuterium and lithium emerged in small quantities, but hydrogen and helium dominated the early universe's composition. The importance of the hydrogen to helium ratio lies in its physics, temperature, density, and the universe's expansion rate. Small variations in these conditions would have altered the elemental proportions. If the universe had cooled faster or slower, the ratios would have shifted accordingly. Therefore, measuring their abundances today offers precise insights into those initial conditions. Currently, about 75% of ordinary matter is hydrogen, and roughly 25% is helium. These ratios are derived from spectral observations of ancient stars, distant galaxies, and cosmic clouds. By analysing the light from these objects, astronomers determine the primordial helium fraction. A denser, hotter early universe fused more neutrons into helium, raising its ratio. A less dense or faster cooling universe produced less helium. This observed ratio acts as a time capsule, indicating the universe's initial conditions, which produced roughly 3/4 hydrogen and 1/4 helium. It aligns with Big Bang predictions, which calculate these proportions based on early universe physics and expansion rates. Thus, the ratio demonstrates the consistency of current cosmological models with observational evidence. Moreover, these abundance ratios support the idea that conditions during primordial nucleosynthesis were uniform throughout the universe, consistent with the cosmological principle. This uniformity aligns with cosmic inflation theory, which suggests rapid, even expansion in the universe's early moments. The ratios also reflect that expansion was influenced by radiation, matter, and energy interplay, as described in the standard cosmological model. Tiny deviations from expected ratios can lead to new discoveries. Small anomalies in helium or deuterium may suggest unknown particles, variations in fundamental constants, or new physics during the universe's infancy. For example, higher than expected helium could hint at additional neutrino types or dark radiation. These subtle clues refine cosmological models, advancing understanding. The primordial element ratios serve as a baseline for cosmic evolution. Over billions of years, stars fused hydrogen into heavier elements, enriching galaxies chemically. However, the original ratios, preserved in the universe's oldest structures, help distinguish initial conditions from subsequent chemical changes. Studying these ratios is akin to reading a pivotal moment in cosmic history, marking the universe's beginning. They connect early particle physics with the larger structure of galaxies, stars, and planets today. The ratios reflect a delicate balance in those first moments, shaping subsequent evolution. Even in chaos, a precise equilibrium emerged, determining the universe's destiny. This underscores the key role of primordial element ratios in cosmology. They serve as a fundamental test of the Big Bang theory, linking observable universe properties to early universe physics. The agreement between predicted and observed ratios affirms the robustness of current cosmological models. In essence, the hydrogen to helium ratio functions as a cosmic relic. It provides direct insight into the universe's earliest moments, revealing the physical conditions then. These ratios are crucial for understanding how a simple, hot, dense state evolved into the complex structured universe we see today. Ongoing observations continually challenge and improve theories. Small discrepancies prompt scientists to revisit assumptions or propose new physics, keeping understanding dynamic. The hydrogen and helium ratios remain essential in unlocking the universe's deepest secrets, fundamental to cosmology's quest to decipher our origins. Once the universe had cooled enough for the first atomic nuclei, primarily hydrogen and helium, to form during primordial nucleosynthesis, a new challenge emerged. How did these nuclei become the neutral atoms that would eventually give rise to stars, planets, and life? The transition from free nuclei to stable, neutral atoms was not straightforward and was hindered by several fundamental barriers. Right after nucleosynthesis, the universe was an incredibly hot, dense plasma of free nuclei and a sea of energetic photons, light particles constantly bombarding everything in sight. During this era, the photons possessed enough energy to strip electrons away from atoms almost as quickly as they tried to combine, a state often described as a photon bath, capable of ionizing atoms almost instantaneously. This intense radiation prevented the formation of neutral atoms because any incoming electron that might have bound with the nucleus was immediately knocked free again by a high-energy photon. Imagine trying to form a delicate snowflake in a blizzard. No matter how many snowflakes you assemble, the fierce wind keeps blowing them apart. Similarly, in the early universe, the relentless bombardment by high-energy photons kept free electrons and nuclei from settling down into neutral atoms. The process was akin to a constant tug-of-war. Ions and electrons could come together momentarily, but the energetic photons would tear them apart just as quickly, preventing stable atomic structures from forming. Another significant barrier was the universe's temperature. During the early 100,000 years after the Big Bang, the temperature remained so high, on the order of several thousand Kelvin, that any stable atom formation was thermodynamically unfavourable. The thermal energy was simply too great. Electrons would remain in an energetic state where they endlessly scattered off nuclei or were repeatedly knocked free. Only as the universe expanded and cooled did conditions become favourable for atoms to stabilise. But even as the universe cooled down to around 3000 Kelvin and the energy of photons dropped enough, another problem arose: the recombination struggle posed by the high number of photons present. Because the universe was still flooded with photons energetic enough to ionize atoms, the newly formed neutral atoms would be overshadowed by radiation trying to ionize them again. This created a sort of standoff. Ions and electrons might try to unite, but the surrounding radiation kept pushing them apart. Over countless interactions, and as the universe continued to cool and expand, the photon density decreased. When the temperature fell below a critical threshold, roughly around 3000 Kelvin, photons no longer had enough energy on average to ionize hydrogen atoms. This was the moment when the universe became transparent, allowing photons to travel freely and light to finally move unimpeded across space, an event we call the surface of last scattering. With fewer energetic photons around, more electrons could finally comfortably bind with nuclei to form neutral hydrogen and helium atoms. The barriers, thermal energy and ionizing radiation, gradually relinquished their grip, making it possible for the matter in the universe to transition from an opaque plasma to a transparent cosmos filled with stable atoms. This pivotal turning point set the stage for the cosmic structures we observe today: galaxies, stars, planets, and ultimately us. Cosmic microwave background radiation, or CMB, provides critical evidence of early atom formation. This faint glow pervades the universe as a relic from when it was hot, dense, and young, just a few 100,000 years after the Big Bang. Initially, the universe was a chaotic mix of energy, particles, photons, protons, neutrons, and electrons, all in an extremely hot, opaque state. Photons couldn't travel far without scattering off charged particles, creating a luminous fog. As the universe expanded and cooled, significant changes ensued. About 300,000 years after the Big Bang, the universe cooled enough for protons and neutrons to combine into nuclei, mainly hydrogen and helium. At this stage, high-energy photons prevented stable nuclei by knocking electrons free, maintaining an opaque ionized plasma where photons constantly scattered off free electrons, preventing light from travelling freely. When the universe cooled below roughly 3000 Kelvin, recombination occurred. Electrons finally combined with protons and helium nuclei, forming neutral atoms. This transition changed the universe from a charged, photon-filled plasma to a transparent cosmos with neutral hydrogen and helium. Once atoms formed, photons experience less scattering, allowing light to traverse space unimpeded. These photons, emitted during recombination, have travelled through the universe ever since. As the universe expanded and cooled further, their wavelengths stretched into the microwave spectrum. Today, scientists detect this relic radiation as the CMB, a uniform faint glow filling space. Studying the CMB offers a snapshot of the universe at the epoch of atom formation. Its stable temperature of about 2.7 Kelvin indicates matter was evenly distributed then. Tiny fluctuations, called anisotropies, reveal regions slightly denser than average, which would later evolve into galaxies, stars, and planets. These fluctuations have provided profound insights into early atom formation. Their properties match predictions from Big Bang models with impressive precision. The pattern of small irregularities supports the idea that, as atoms formed and photons could travel freely, density differences during that era seeded cosmic structures. The CMB confirms the universe's hot, dense origins and provides direct evidence for the transition from a photon-dominated state to a universe filled with neutral matter. Its uniformity, slight anisotropies, and spectrum reflect the timing of atom formation in cosmic history. Essentially, the CMB is like a cosmic baby photo, capturing the universe when hydrogen and helium atoms appeared. Its discovery and study have validated current theories of early atom formation. Without it, understanding how and when atoms emerged during cosmic evolution would be much harder. This radiation exemplifies how observing faint signals across vast distances reveals cosmic secrets. The CMB traces back to when the universe shifted from a luminous plasma to a transparent realm where atoms could form and exist freely. That transition was pivotal, leading to stars, planets, and ultimately, life. In summary, The CMB provides crucial evidence of the universe's earlier stages. Its properties, small fluctuations and spectrum, align with models predicting neutral atom formation. The detection of this background opened a window into the universe's infancy, helping scientists understand how and when the first atoms formed. The significance of the CMB lies in its role as an observable remnant, a cosmic fingerprint of early atom formation, confirming the predicted timeline of cooling, nuclear synthesis, and recombination. Its near-uniform temperature, punctuated by slight variations, reflects initial uniformity and tiny density differences that later grew into cosmic structures. Precise measurements have demonstrated that the universe experienced a critical phase change, when it cooled enough for atoms to form and light to travel freely for the first time. This process rendered the universe transparent, allowing photons to escape their tangled state. The CMB's detailed features, including tiny temperature anisotropies, encode information about the universe's early conditions. These observations align with theoretical models of atomic formation and subsequent large-scale structure development. In conclusion, the cosmic microwave background is a direct, observable remnant from when atoms first appeared in the universe. Its properties, uniform glow, fluctuations, and spectrum, provide strong support for our understanding of early cosmic history, particularly the epoch of recombination. As a relic radiation, it reveals how the universe transitioned from a hot plasma into a transparent space filled with neutral atoms, forming the basis for all cosmic structures today. The recombination era is a pivotal chapter in the story of our universe, marking a time when things truly began to change in a profound way. Imagine a universe filled with a hot, dense plasma of free electrons and nuclei, protons and neutrons, zipping around in a frenetic dance. During this period, the universe was incredibly hot, so energetic that electrons couldn't settle into stable atoms. Instead, they constantly got knocked away from nuclei, creating a fog of charged particles that kept radiation from traveling freely. This fog made the universe opaque, like a dense cloud allowing no light to escape. But as the universe expanded, it also cooled, gradually losing energy. When the temperature dropped enough, something remarkable happened. Electrons found a more stable environment and combined with protons to form neutral hydrogen atoms in a process we call recombination. This is not just about electrons and protons coming together, it's about a universe transforming from an opaque glowing soup to a transparent cosmos. Suddenly, photons, the particles of light, were no longer being scattered relentlessly and could travel freely across space. This event changed everything because it allowed light to finally travel unimpeded, giving birth to what we now call the cosmic microwave background radiation, or CMB. Why does this matter so much? Because the CMB is essentially a leftover echo of that frozen epoch, a snapshot of the universe at roughly 300,000 years after the Big Bang. It's the oldest light we can observe, acting like a cosmic baby picture. When scientists detect fluctuations or tiny variations in this background radiation, it's as if they are peering back in time to see the universe in its infancy. These subtle variations are the fingerprints of the initial density fluctuations, tiny variations in matter distribution that would eventually grow into galaxies, stars, and planets. Recombination set the stage for a universe brimming with structure. Before this era, all matter was tangled in an energetic cloud. Afterward, it could start to clump together under gravity. The formation of neutral atoms liberated the universe from its dense opacity, allowing light to journey across vast distances. This unlocked a new chapter in cosmic evolution, a universe where photons could travel freely, carrying information about the initial conditions from which all cosmic structures emerged. Without the recombination era, the universe would have remained a relentlessly hot, glowing fog. No stars, no galaxies, no planets, and no life. This event effectively painted the first clear picture we have of the universe's early moments. It allowed us not just to confirm the Big Bang Theory through the discovery of the CMB, but also to understand how matter transitioned from a state of chaos to a more ordered, structured cosmos. In a way, recombination was like the universe's grand finale, taking a hot, opaque universe and turning it into a transparent stage where the cosmic story could unfold. It was during this quiet, cool transition that the seeds for all future cosmic evolution were sown. From that moment, matter could gather, clump, and eventually ignite into the stars and galaxies that make up the universe we see today. The recombination era is, therefore, not just a historical milestone. It's a turning point that set the entire universe on the path towards complexity and, ultimately, life itself. As the universe continued to expand and cool, a remarkable transformation was on the horizon. During the first few 100,000 years after the Big Bang, the universe was a hot, dense plasma of free particles, protons, neutrons, electrons, and photons all swirling together in a fiery stew. In this primordial state, the energy was so intense that atoms, as we know them today, couldn't exist. Instead, particles constantly collided and exchanged energy, preventing the formation of stable, neutral atoms. But as the universe stretched and cooled further, reaching temperatures of roughly 3000 Kelvin, conditions began to change dramatically. Electrons, which had been bouncing around all over the place, started to feel the pull of the positively charged nuclei, protons primarily, with some neutrons thrown into the mix. This was the moment when the universe transitioned from a plasma to a state where atoms could actually form. At these cooler temperatures, electrons, tiny negatively charged particles, began to stick to protons, which carried a positive charge. The process is somewhat akin to a dance. The electrons, moving around rapidly in the high-energy environment, started to slow down slowly as the universe expanded and cooled, losing enough energy to be captured by the nuclei. When an electron finally teamed up with a proton, a neutral hydrogen atom was born. This wasn't just a casual pairing. For an electron to be captured and form a stable bond with the nucleus, the energy levels had to be just right. In the early universe, the electrons had energies spread out across a range of values, described by a distribution similar to a spectrum of colours. As the universe cooled, the energy of the electrons decreased enough that a significant number of them could bind to protons, dropping into the lowest available energy state, what scientists call the ground state. But the story isn't as simple as just electrons attaching to protons. Because free electrons are negatively charged and protons are positive, their attraction is very strong. However, in the hot plasma environment, any electron that managed to capture a proton could be hit by a photon, with enough energy to knock it back out again. Only when the universe cooled enough that photons no longer had enough energy to re-ionize the atoms did the atoms stay stable. This transition is famously known as recombination, like a long cool evening when electrons and nuclei finally come together and settle down. As the electrons combined with nuclei, the universe became increasingly transparent because the free electrons that were scattering photons in all directions were now locked inside neutral atoms. Photons, particles of light, could travel unhindered across vast stretches of space, creating the cosmic microwave background radiation that still hums softly today as a relic of this pivotal epoch. The formation of neutral atoms marked a turning point. Suddenly, the universe was no longer a cloudy, opaque fog. Instead, it turned transparent, allowing the light to stream freely through the cosmos. This liberated photon bath became what we observe today as the faint uniform glow of the cosmic microwave background. With the universe now filled with neutral hydrogen and helium, the stage was set for the next chapter in cosmic history: stars, galaxies, and eventually planets and life. These neutral atoms gathered under the influence of gravity, pulling together to form the dense regions that would ignite nuclear fusion and give birth to the luminous structures that shape our universe. It's a story of patience and gradual change, where cooling temperatures and quantum mechanics joined hands to turn a searing plasma into the calm, glowing cosmos we observe now. As the universe continued to expand and cool, a remarkable event known as recombination began to unfold. But what exactly causes matter to become transparent to radiation during this pivotal moment? To understand this, we need to delve into the behavior of particles and light in the early universe. In the hot, dense state immediately after the Big Bang, the universe was filled with a sizzling plasma composed of free electrons, protons, and photons, the particles that carry light. In this environment, photons couldn't travel far before colliding with free electrons. They were constantly scattered, making the universe opaque. Imagine trying to see through a foggy window. The dense particles prevent light from passing through freely. During this phase, photons were bouncing around ceaselessly, unable to escape, which kept the universe opaque and preventing us from seeing back to those moments. As the universe expanded, it cooled. The temperature dropped from millions of degrees down to a few thousand degrees Kelvin. This cooling had a profound effect on the particles contained within the universe. For protons and electrons, it meant they could begin to combine and form neutral hydrogen atoms, the most common element in the universe. But this transition isn't just about atoms forming. It influences how photons interact with matter. When electrons and protons combine to form neutral hydrogen, they no longer carry an electric charge, making them much less effective at scattering photons. In essence, the fog begins to lift because the free electrons that once kept photons bouncing around are now trapped within neutral atoms, which are much more transparent to light. Without free electrons to scatter them, photons can now travel long distances in space. The universe effectively becomes transparent, a moment when light could finally stream freely through what was once a dense, opaque plasma. But why does this transition happen at a specific moment? It all comes down to the balance between the likelihood of photons being scattered and the decreasing number of free electrons in the universe. At high temperatures, the rate of ionization is kept high. Atoms are constantly being torn apart by energetic photons. As the universe cools, photons no longer have enough energy to ionize many hydrogen atoms. This means that a significant decrease in free electrons occurs because electrons are combining with protons faster than they're being destroyed by energetic photons, leading to a rapid decrease in the universe's opacity. This recombination process is governed by atomic physics. The formation of neutral atoms is a quantum process that depends on temperature, density, and the interplay of electromagnetic forces. Once a substantial fraction of hydrogen atoms form, the mean free path of photons increases dramatically. These photons, which previously were trapped in a dense plasma, now have the freedom to travel vast stretches of space. This transition from opaque to transparent is what enables the universe to become visible to us. The photons released during recombination journey across cosmic distances and finally reach us as the cosmic microwave background radiation, the faint afterglow of that ancient epoch. It's like the universe's first light, revealing a snapshot of the cosmos when matter first allowed photons to escape their cosmic prison. In short, matter becomes transparent during recombination because the formation of neutral atoms drastically reduces free electrons, which are responsible for scattering photons. With fewer free electrons available, photons can travel unimpeded, crossing immense distances and carrying with them the story of the universe's earliest luminous moments. It's a momentous turn in cosmic history, when the universe's veil of opacity was lifted, unveiling a universe ready to be observed, understood, and explored. As the universe continued to expand and cool in the aftermath of the Big Bang, a pivotal transition was unfolding. For hundreds of thousands of years, the universe was a searing, opaque fog of free electrons and protons, bouncing radiation around in a chaotic dance. Photons, the particles of light, couldn't travel far without scattering off these charged particles, making the universe a brilliant but impenetrable plasma. But then, something extraordinary happened. Electrons and protons began to team up to form the first neutral atoms. This process, known as recombination, took place when the universe cooled enough, down to about 3000 Kelvin, that electrons could be captured by protons without immediately being knocked loose again by energetic photons. When free electrons combined with protons, they formed hydrogen atoms, the simplest and most abundant element in the universe. This transformation was like clearing the fog. Suddenly, photons could travel freely across space for the first time in hundreds of thousands of years. Before recombination, the universe was a dense hot soup where light was constantly scattering and rescattering. But once neutral atoms formed, the universe's opacity dramatically decreased. Because neutral hydrogen doesn't scatter light in the same way, photons could stream freely through the cosmos, heading out into the vastness unimpeded. This released a flood of radiation into space, a faint glow that has persisted ever since. Today, we recognize this as the cosmic microwave background radiation, a faint, uniformly spread glow filling the universe. It's a kind of cosmic photograph, capturing a moment frozen in time when the universe shifted from an opaque to a transparent state. This moment was a turning point, marking the universe's transition into its next chapter. With photons now free to journey across space, the universe entered what's often called the Dark Ages, a time before stars and galaxies ignited. But the brief silence was disrupted by the gravitational pull of tiny irregularities formed during the earlier quantum fluctuations and cosmic inflation. These irregularities served as the seeds for the universe's large-scale structure: galaxies, clusters, and superclusters. The cosmic microwave background is like a snapshot of the universe just 380,000 years after the Big Bang, an image of the universe in its infancy. It's remarkably uniform, bathing the cosmos in a nearly even glow, but with minuscule variations, tiny temperature differences that delineate the universe's initial density fluctuations. These slight unevennesses are what would, billions of years later, grow under gravity's influence to create the grand structures we observe today. The faint glow of the cosmic microwave background, stretched to microwave wavelengths by the universe's expansion, carries within it invaluable clues about the early universe. Its existence confirms our understanding of how atoms formed when the universe cooled, and it serves as a powerful cosmic relic, proof that from this primordial and seemingly featureless start, the universe has transformed into the rich tapestry of stars, galaxies, and nebulae we see today. So, the formation of neutral atoms was more than just a chemical milestone. It was the key that unlocked the universe, allowing light to break free from its primordial prison. That liberation of photons created the cosmic microwave background, a faint whisper of the universe's earliest moments, an ancient glow still shimmering across space, silently telling the story of creation itself. As the universe continued to expand and cool, it reached a pivotal moment known as recombination, when the first atoms finally began to form. But what exactly allowed this to happen? The answer lies in the delicate interplay between temperature and density, two fundamental factors that dictated whether subatomic particles could come together and form more complex structures. Imagine the universe's early moments as a blazing, searing furnace, where temperatures soared to hundreds of billions of degrees Fahrenheit. At these extremes, particles like protons and neutrons zipped around at breakneck speeds, their energy so high that any attempt at forming atoms was futile. Over time, as space expanded, the universe cooled. This cooling wasn't abrupt but gradual, allowing the energy levels of particles to drop steadily. When temperatures fell below roughly 10,000 Kelvin, conditions became suitable for protons and electrons to start combining. But temperature wasn't the only player in this cosmic game. Density, the measure of how much matter is packed into a given volume, was equally crucial. In the early universe, the density was incredibly high, like a dense fog of particles swirling in all directions. High density meant particles collided often, which generally helped in forming stable atoms. However, it also meant that free electrons and protons were constantly being knocked apart by energetic photons, particles of light themselves. This intense photon bath kept the universe opaque, with photons frequently scattering off free electrons, preventing light from travelling freely and hindering atoms from establishing a stable existence. As the universe continued to expand and cool, the density of particles decreased. Lower density meant that particles collided less frequently, giving electrons a better chance to settle into atom-like structures without being immediately stripped away by energetic photons. At this stage, the temperature dropped enough that the energy of photons was no longer sufficient to ionize hydrogen atoms, that is, to knock electrons loose once again. When the photon energies fell below the ionization energy of hydrogen, a remarkable transition occurred. Protons and electrons could now combine to form neutral hydrogen atoms. This process is often described as a dance between energy and matter. When the temperature dips below a critical threshold, the kinetic energies of particles are low enough that electromagnetic attraction can hold electrons tightly around protons. Meanwhile, the decreased density reduces the likelihood of photons scattering off free electrons, allowing nearby electrons and protons to bond for longer periods, forming stable atoms. This transition dramatically changed the universe's transparency. Photons, no longer frequently scattered by free electrons, could now travel freely and eventually reach us as the cosmic microwave background radiation we observe today. If the universe had cooled too slowly or remained too dense for too long, atoms might have formed later or only in isolated pockets. Conversely, if it cooled too rapidly or became too diffuse too quickly, atoms might have struggled to form altogether. The exact balance, where temperature fell below the critical point while density decreased enough, created a sweet spot where atom formation could flourish. This delicate equilibrium allowed the universe to transition from a hot plasma to a vast, transparent cosmos, filled with the building blocks of galaxies, stars, and planets. In a nutshell, temperature and density didn't just influence the timing of atomic formation, they dictated the very nature of the first atoms to emerge. Cooler temperatures meant less energetic, more stable conditions for electrons to settle around protons. The right density ensured that particles interacted frequently enough to bond, but not so often, that energetic photons kept breaking those bonds apart. Together, these factors set the stage for the universe's first true atoms, unlocking a new chapter in cosmic evolution and laying the groundwork for everything that was to come. After the universe cooled enough for electrons and protons to combine into neutral hydrogen, recombination, it entered the Dark Ages. This was a cosmic twilight before stars and galaxies formed, shrouded in mystery. During these early hundreds of millions of years, the universe was a vast, dark, mostly uniform expanse, illuminated only by faint residual glow from the Big Bang, known as the cosmic microwave background radiation. The universe was filled with a diffuse cooling fog of neutral hydrogen gas stretched across immense distances. Without stars or galaxies shining, there was no light to break the darkness. It was essentially a silent ocean, with tiny fluctuations in density, ripples from quantum fluctuations in the earliest moments, amplified by inflation. These variations served as seeds for future structures. In this era, the universe was largely homogeneous, but not perfectly so. Slight overdensities in hydrogen created tiny gravitational wells. Over millions of years, these regions attracted more matter, growing in mass and depth. Without luminous objects, this process was invisible, a quiet build-up with gravity slowly shaping the universe from a dark, uniform mist. Temperature decreased as the universe expanded. The hot, dense, early universe transitioned into a cooler, more diffuse state. Hydrogen gas, initially ionized after the Big Bang, was now neutral, transparent, and free-floating. Without stars or other light sources, the universe was practically invisible, detectable only through faint signals like the cosmic microwave background or subtle gravitational effects. Despite the darkness and silence, this was a dynamic period. Matter clumping under gravity was slow but relentless. Tiny gravitational wells grew more significant over hundreds of millions of years. small higher density regions gathered gas, increasing in mass and depth. These regions would eventually collapse under their own gravity, forming the first stars and ending the Dark Ages. This epoch marked the transition from ionized, opaque plasma to neutral, transparent gas, allowing light to travel freely through space. This was a pivotal change, ending cosmic darkness and moving toward a luminous universe. Yet, it would still be many millions of years before stars appeared, bringing light back into the cosmos and ending the Dark Ages. During this silent, dark chapter, the universe was a cold, mostly empty expanse, slowly transforming from a uniform mist of gas into star and galaxy nurseries. It was a universe in transition, waiting patiently in darkness for the spark that would ignite a new era of cosmic evolution. The first star's emergence would eventually light up the universe, creating galaxies, planets, and conditions for life. In this period, the universe's structure was starting to emerge, driven by gravity pulling matter into tiny potential wells. Slowly but surely, these fluctuations grew, setting the stage for the next epoch. The process was silent, yet relentless, shaping the universe's large-scale structure. The period marked the shift from a dark, featureless cosmos to one filled with potential luminous objects and complexity. Ultimately, the Dark Ages was a silent transitional era, an essential phase in cosmic history, when the universe was gradually preparing for the emergence of light, stars, and structure. It was a time of waiting, in darkness, for the universe to awaken. When the first stars finally appeared, they illuminated the cosmos, ending the Dark Ages and beginning the luminous, structured universe we observe today. After the universe cooled enough for atoms to form, a remarkable process began that would eventually give birth to galaxies, stars, and planets. Initially, the universe was a vast, nearly uniform expanse, filled with hydrogen and helium gases, drifting through space almost like a gentle, glowing fog. But this uniformity was subtly imperfect. Tiny variations in the density of this primordial gas, ripples in the fabric of the early universe, had emerged from quantum fluctuations during the inflationary epoch. These minuscule differences, less than a part in 100,000, seeded regions where atoms were slightly more concentrated than their surroundings. Gravity, the force that governs the dance of celestial bodies, started to play a crucial role in the evolution of these tiny irregularities. Despite their small scale, these overdense regions had a slight advantage. More matter was packed into them compared to the surrounding space. Over cosmic timescales, gravity worked tirelessly, pulling more gas into these regions of higher density. Think of it as a cosmic game of catch-up. These denser patches began to attract more and more hydrogen and helium atoms, strengthening the gravitational pull within. Initially, the universe's expansion worked against these pockets of matter, stretching everything apart and preventing any significant clumping. But as the universe expanded and cooled, the gas within these overdense regions started to slow down relative to the vast cosmic expansion. Once the pressure forces from the hot, diffuse gas began to diminish, gravity was free to dominate. This transition was like a gentle tipping point. Once gravity gained the upper hand, it caused the overdense regions to grow even denser and more compact. Within these growing clumps, particles of gas started to move inward, pulled by the increasing gravitational pull. As the matter accumulated, certain regions became dense enough that their gravity could overcome the internal pressure of the gas. Within these regions, tiny differences in density grew into large, dense clouds of gas, what astronomers call atomic gas clouds. These clouds were the earliest nurseries of stars and galaxies, the cosmic cradles where matter began to coalesce into more complex structures. The process of clumping was not uniform across the universe. Variations in density meant that some regions became denser much sooner than others, leading to a patchwork of gas clouds in different stages of collapse. Some of these clouds were relatively small, while others, due to the accumulation of matter over longer periods, grew into enormous complexes containing billions of times the mass of our Sun. Over hundreds of millions to billions of years, these gas clouds served as the fertilized fields of star formation. Cooling played an essential role in this transformation. As gas clouds gathered more matter, they heated up due to gravitational energy transforming into heat. Imagine compressing a sponge. It gets hotter as it gets squeezed, but for these clouds to collapse further and eventually give birth to stars, they needed to shed this heat. This cooling occurred through the emission of radiation, especially in the form of specific wavelengths of light called spectral lines. As the gas cooled, it lost thermal energy, allowing gravity to pull matter inward more effectively. The denser the gas became, the more efficient this cooling process was, leading to runaway collapse in what are known as gravitational instabilities. Some of these gas clouds then fragmented into smaller regions, setting the stage for star formation. As gravity continued to pull inward, the cores of these clouds grew hotter and denser, eventually igniting nuclear fusion and giving birth to the first generation of stars. These stars became the cosmic engines that would forge heavier elements and sculpt the universe we see today. In short, The journey from a nearly uniform universe filled with atomic gases to a universe teeming with structured complexity was driven by gravity's relentless pull on the tiniest density fluctuations. Over time, these slow but persistent clumping processes shaped the vast cosmic web, turning the universe's early fog into the intricate tapestry of galaxies, stars, and planets that continues to fascinate us. After the universe cooled enough for neutral atoms, mainly hydrogen and helium, to form, a new chapter in cosmic history began, one filled with quiet anticipation. The universe changed from a hot, dense plasma to a vast, dark expanse sprinkled with tiny fluctuations in density, minute variations in matter, distribution from early cosmic inflation. These irregularities served as seeds for all future structures. How did these seemingly insignificant irregularities grow into luminous stars and shimmering galaxies? Gravity, the universe's relentless sculptor, was key. It's an attractive force pulling matter together, even in a universe initially nearly uniform. Slight overdense regions exerted a gravitational pull on surrounding particles. Over immense time, these regions gathered more matter, becoming the cosmic nurseries where galaxies would form. As more matter accumulated, gravitational wells deepened, pulling in gas and dark matter, a process called gravitational instability. It's akin to ripples in a pond amplifying into waves, with density fluctuations developing into nascent galaxies. As these regions grew denser, gravitational collapse intensified. The early universe's energetic particles and ultraviolet radiation kept some regions ionized, preventing collapse for a time. But as expansion continued and the universe cooled, gas within dense pockets began to lose energy. When gas clouds cool, their internal pressure decreases, making them more susceptible to collapse. Once sufficiently cooled, these clouds became unstable, collapsing inward to form dense cores, the cradles of star birth. Within these collapsing clouds, multiple processes occur simultaneously. Rising density converts potential energy into heat. This is gravitational heating. To continue collapsing, the gas must shed this heat via radiative cooling, where atoms and molecules emit photons, light, allowing further contraction. Hydrogen and helium were the main coolants in the primordial universe. As they radiated energy away, pockets of gas grew denser and colder, creating ideal conditions for stars to ignite. The first stars, population 3 stars, formed from pristine hydrogen and helium without heavier elements. Due to limited cooling options, these stars were massive, often many times the Sun's mass, and burnt their fuel rapidly. Their size and brightness meant they lived only a few million years before ending in supernova explosions. These supernovae did more than mark the stars' deaths. They enriched the surrounding gas with heavier elements like carbon, oxygen, and silicon. This process, called chemical enrichment, was vital for subsequent star and planet formation. Heavier elements enabled more efficient cooling, leading to the birth of smaller, more stable stars and diverse celestial objects. Meanwhile, gravitational pull continued to act on larger scales. Gas, stars, and dark matter clustered into the first galaxies, vast collections of hundreds of billions of stars orbiting a common center. These early galaxies appeared as small, irregular shapes, smudgy patches of light. Over time, through interactions, mergers, and ongoing gas accretion, they evolved into the spiral and elliptical galaxies we see today. Star and galaxy formation was fueled by a cycle of collapse, heating, cooling, and fusion. Over billions of years, this process created the cosmic tapestry, filled with countless stars, sprawling galaxies, and complex structures. It's a story of gradual accumulation, dynamic interactions, and gravity's relentless influence, a cosmic dance transforming primordial chaos into the luminous universe we observe. The universe's initial irregularities grew through gravitational instability, leading to the formation of dense gas clouds. As these clouds cooled and collapsed, they formed the first stars, which processed and dispersed heavy elements upon death. These elements allowed subsequent stars and galaxies to evolve into the complex structures we see today, demonstrating an ongoing cosmic evolution driven by gravity, cooling, and nuclear fusion. As the universe cooled and expanded following the formation of the first nuclei, it entered a new chapter, one where the glow of the Big Bang gradually faded, and the early cosmos was filled with a vast, dark expanse of neutral hydrogen gas. These primordial clouds of hydrogen, simple yet fundamental, were like silent witnesses to the incredible events unfolding around them. But everything was about to change with the birth of the first stars. These first stars, sometimes called population 3 stars, were nothing like the familiar stars we see today. They were colossal, often many times the mass of our sun, burning fiercely with extraordinary brightness and energy. Their formation was driven by the gentle pull of gravity as regions of hydrogen gas became denser and denser. Over time, these dense pockets ignited nuclear fusion in their cores, transforming hydrogen into helium and unleashing torrents of energy. When these luminous giants ignited, they didn't just shine in isolation. They stirred the quiet darkness of the universe itself. One of the most profound ways these first stars influenced their surroundings was through their intense radiation. As these stellar giants blazed with incredible brightness, they emitted copious amounts of ultraviolet light. This radiation didn't just illuminate the cosmos, it actively interacted with the surrounding hydrogen. When high-energy photons from the stars encountered neutral hydrogen atoms, they could strip electrons from these atoms, ionizing the gas, turning it from a neutral state into a plasma of protons and electrons. This process, known as reionization, effectively reshaped the universe's earlier scaffolding. Imagine a vast, frigid field of hydrogen, silent and still. Then, suddenly, a blazing star appears, its ultraviolet radiation piercing through the darkness. The radiation energizes the hydrogen atoms, knocking their electrons loose. As a result, large volumes of the universe's simplest element become ionized, creating bubbles of plasma that expand and merge as more stars form and shine. This epoch of reionization transformed the universe's appearance, rendering it more transparent to high-energy photons and paving the way for the universe to become increasingly hospitable for the development of galaxies, stars, and planetary systems. But the influence of the first stars didn't stop at ionization. Their energetic radiation heated the surrounding gas, causing it to expand and become more diffuse. This heating could suppress new star formation, creating a complex interplay where some regions were pushed back into a state of silence, while others became cradles for new stars. The pressure from this heated gas created a feedback loop. Larger, brighter stars emitted more radiation, further ionizing and heating the hydrogen around them, shaping the large-scale structure of the universe. In addition, the first stars contributed to cosmic chemistry in profound ways. When these giants exhausted their fuel, an event marked by spectacular supernova explosions, they dispersed newly forged heavy elements and metals, elements heavier than helium, into the surrounding environment. These metals would eventually seed subsequent generations of stars and planets, fostering the diversity of matter necessary for the formation of complex structures, including life. The intense energy during supernovae also generated shock waves, compressing nearby hydrogen and triggering the formation of new stars in a cosmic cycle of birth and death. Moreover, the enormous energy output and the disruptive force of these supernovae played a critical role in clearing out residual gas from certain regions, influencing the distribution and evolution of matter across the universe. It was through these tumultuous energetic events that the universe transitioned from a dark, neutral universe to a luminous cosmos, filled with active star-forming regions, galaxies, and intricate cosmic web structures. So, in essence, the first stars didn't just flicker into existence and fade away. They were catalysts that transformed the universe's simplest elements into a more complex, dynamic environment. Their radiation ionized neutral hydrogen, their energetic winds and supernovae dispersed heavy elements, and their formation and death created a feedback system that dictated the early evolution of cosmic structures. Without these pioneering stellar engines, the universe would have remained a dark, featureless expanse, a silent universe waiting for its first lights to ignite the complex cosmos we observe today. When considering the earliest structures, first stars, galaxies, and clusters, there's a wealth of observational evidence that reveals how they formed. Scientists have used powerful telescopes and instruments for decades to gather clues from the universe's infancy. A key piece of evidence is the cosmic microwave background radiation, CMB. This faint glow, observed when the universe was just over 300,000 years old, fills the cosmos. It isn't random noise, but a map of tiny temperature fluctuations or anisotropies that correspond to regions of slightly higher or lower density. These irregularities are like fingerprints left by primordial quantum fluctuations amplified during cosmic inflation, signaling the seeds of future structures that grew into galaxies and clusters. Satellites such as COBE, WMAP, and Planck measured these variations with great precision, confirming that the universe started out remarkably smooth, yet with slight irregularities providing the scaffolding for all the complexity we observe today. Another important line of evidence comes from galaxy surveys. When we look into space, we see galaxies arranged in vast filaments, walls, and voids, a cosmic web stretching across hundreds of millions of light years. Redshift surveys, including the Sloan Digital Sky Survey, mapped millions of galaxies, revealing their large-scale structure. These observations support models predicting that matter, initially dispersed by quantum fluctuations, clumped under gravity to form the cosmic web we now observe. The distribution and clustering patterns of galaxies align closely with simulations based on dark matter, dark energy, and early universe physics, providing a direct link from initial irregularities to present-day structures. gravitational lensing offers another vital window into early universe structures. Massive objects like galaxy clusters warp space-time, bending light from background objects. Studying these distortions allows astronomers to map dark matter, the invisible framework underlying structure formation. These maps reveal concentrations of matter tied back to initial fluctuations, offering a direct view of how matter gathered over billions of years. The detection of ancient stars and distant galaxies also supports these ideas. When we look farther back in time, we observe the universe when it was just a few 100 million years old, with its first luminous objects. Telescopes like Hubble have captured images of these early galaxies. Their characteristics, sizes, shapes, and star populations fit with models of structure formation that originate from initial quantum fluctuations, linking early irregularities to initial galaxy formation. Finally, the distribution of primordial elements, hydrogen, helium, and lithium, provides additional evidence. These light elements formed during nucleosynthesis in the early universe, and their relative abundances match predictions based on density fluctuations and gravitational clustering. The observed elemental ratios support models tying initial fluctuations to the universe's subsequent development. All these threads, tiny temperature fluctuations in the CMB, large-scale galaxy clustering, gravitational lensing maps, observations of ancient galaxies, and primordial element abundances, form a cohesive picture. Each piece reveals how the universe's earlier structures emerged from quantum ripples, grew under gravity, and set the stage for the cosmos we see today. Understanding how atoms come into being and stay stable requires a closer look at the fundamental forces that govern everything in the universe. These invisible yet powerful forces are the architects behind the structure of matter, guiding how particles interact, combine, and form the building blocks of everything we see around us. Let's start with gravity. It's the weakest of the four fundamental forces, but has an extraordinary reach that shapes large-scale structures. In the context of atoms, gravity mainly plays a starring role when it comes to massive objects, stars, planets, and galaxies, pulling matter together into dense centers where nuclear fusion ignites stars. On the scale of individual atoms, though, gravity is negligible. The other forces take the spotlight. Still, gravity's influence on the cosmic stage helps us understand the grand organization that ultimately allows atoms to exist within stars and planets, where elements are forged and passed into space, seeding future generations of atoms. Electromagnetism, on the other hand, is a dominant force at the atomic level. It arises from electric charges, protons carrying positive charge and electrons carrying negative charge. The attraction between these opposite charges binds electrons to nuclei, creating the atom's core structure. Think of the atom as a tiny solar system. The nucleus sits at the center, containing protons and neutrons, while electrons whirl around in defined regions called orbitals. The electromagnetic force not only keeps electrons tethered to the nucleus, but also governs how atoms interact with each other. When atoms bond, their outermost electrons interact through electromagnetic forces, forming chemical bonds, covalent, ionic, or metallic, building molecules that make up all matter. Then there's the strong nuclear force, perhaps the most fascinating of them all. It's incredibly powerful at very short ranges, on the order of a femtometer, which is a millionth of a billionth of a meter. This force acts specifically between protons and neutrons within an atomic nucleus, binding them into a tight, stable core. Without the strong force, protons, each bearing positive charges, would repel each other fiercely due to electromagnetic forces, causing nuclei to break apart. The strong force overcomes this repulsion at close distances, gluing protons and neutrons together in a delicate balance that determines the stability of an element. It's responsible for the variety of nuclei, some stable, some unstable, that define different elements and isotopes. The weak nuclear force is the final piece of this puzzle. It's not involved in holding nuclei together, but plays a critical role in certain nuclear processes, especially radioactive decay. For example, in beta decay, a neutron transforms into a proton by emitting an electron, and an antineutrino via the weak force. This process is vital in the cosmic production of elements and the evolution of stars. The weak force also has profound implications for the fundamental symmetry of particles and the overall evolution of the universe. Each of these forces influences not only how atoms form, but also how they behave. The electromagnetic force ensures electrons are held in specific energy levels around the nucleus, giving atoms their unique properties and spectral lines. The strong force ensures nuclei stay intact, defining the identity of elements and their isotopes. The weak force enables certain nuclear transformations, fueling stars and shaping the landscape of elements in the universe. That intricate dance between these fundamental forces crafts the delicate stability of atoms. Without the electromagnetic attraction, electrons wouldn't be tethered to the nucleus, and atoms would disintegrate. Without the strong force, nuclei would be unbound and largely non-existent. Together, these forces choreograph matter's emergence from the quantum chaos that grew out of nothing, forming the atoms that eventually became everything: the planets, the life forms, and even us. It's a cosmic interplay so finely tuned that from seemingly nothing, a universe rich with structure and complexity could flourish. The electromagnetic force is one of the four fundamental interactions in nature, along with gravity, the strong nuclear force, and the weak nuclear force. It shapes the universe on both microscopic and macroscopic scales. This force is responsible for electromagnetic interactions between charged particles, governing attraction or repulsion. Its effects are everywhere, from electrons attracted to protons in atoms to light behavior and electromagnetic fields powering technology. Crucially, it underpins the formation and stability of atoms, molecules, and all matter in the universe. At the atomic level, the electromagnetic force holds electrons bound to the nucleus. An atom comprises a nucleus of protons and neutrons, with electrons orbiting around it. Protons are positively charged, electrons are negatively charged. The electromagnetic force causes attraction between these opposite charges. Without this attraction, electrons would drift away, making atoms unstable and unable to maintain structure. This binding ensures the existence of stable atoms, the building blocks of all matter. The strength of the electromagnetic force at the atomic scale is immense, but acts over relatively long distances, on the order of nanometers. This enables electrons to occupy specific energy levels, or orbitals, where the probability of finding an electron is highest. Electromagnetic attraction pulls electrons toward the nucleus, maintaining atomic integrity and defining size and properties. These energy levels result from a balance between electromagnetic attraction and quantum electron behavior. When electrons absorb or emit energy moving between levels, atomic spectra are produced, distinctive fingerprints for each element. Beyond atomic stability, the electromagnetic force is central to chemical bonding, which creates molecules from atoms. As atoms approach, their electrons interact through electromagnetic forces, leading to sharing, transferring, or rearranging electrons. This results in different bonds. Covalent bonds form when atoms share electrons, creating molecules held together by electromagnetic attraction between shared pairs and nuclei. Ionic bonds form when electrons transfer from one atom to another, creating ions that attract each other electrostatically. Metallic bonds involve a sea of delocalized electrons holding metal atoms together. For example, in water, H2O, the oxygen atom with higher electronegativity, pulls shared electrons closer, creating a polar molecule. This causes a partial negative charge near oxygen and partial positive charges near hydrogen atoms. This polarity arises from electromagnetic interactions and explains water's unique properties: cohesion, adhesion, surface tension, and high boiling point. Such properties are vital in biological systems, affecting nutrient transport and cellular processes. Electromagnetic forces also govern interactions between molecules, influencing material properties and biological functions. They dictate how molecules recognize and bind to each other, facilitating biochemical reactions, protein folding, and DNA stability, all essential for life. Electromagnetic interactions extend to larger phenomena, such as the propagation of light, electromagnetic radiation, and the behavior of astronomical bodies, highlighting their fundamental role in shaping the universe. If the electromagnetic force were much weaker, atoms wouldn't hold electrons close, leading to unstable, non-reactive matter and preventing complex molecules from forming. Conversely, a stronger force could cause atoms to bond too tightly or in incompatible configurations, hindering biological diversity. The fine balance of electromagnetic attractions and repulsions allows a universe rich in chemicals, structures, and life. In summary, the electromagnetic force is essential because it creates the attractive and repulsive interactions necessary for atoms to form and stay stable. It mediates bonding, leading to molecules and materials. Without it, matter would be amorphous, chemistry as we know it would be impossible, and complex biological structures wouldn't emerge. It is the invisible glue binding the universe at the smallest scales, integral to everything around us. The electromagnetic force, arising from charged particles interacting across space, is fundamental in creating the complex structured universe. It enables stars, planets, life, and consciousness to emerge, shaping the fabric of reality. The strong nuclear force is one of the universe's fundamental interactions, crucial for holding atomic nuclei together. To understand this, consider that an atom's nucleus contains protons and neutrons packed tightly. Protons are positively charged, neutrons are neutral. Since like charges repel, one might expect protons to push each other apart. Yet, they don't. Instead, the strong nuclear force acts as an invisible, powerful glue that keeps protons and neutrons bound. overcoming electrostatic repulsion. This force is called strong, because it is the strongest among the four fundamental forces, far more potent than gravity, electromagnetism, or the weak nuclear force. Its strength is most evident over a very short range, about 1 to 2 femtometers, roughly the size of an atomic nucleus. Beyond this tiny distance, the strong force diminishes rapidly, making it a short-range but highly powerful interaction. At the subatomic level, protons and neutrons are themselves bound by the strong force, rooted in quantum chromodynamics, QCD. QCD describes how quarks, the fundamental constituents of protons and neutrons, interact via particles called gluons. Gluons act as messengers, exchanging energy and momentum between quarks, effectively locking them inside nucleons. Within protons and neutrons, quarks are tightly bound by the strong force, the most fundamental manifestation of it. However, the strong force doesn't only operate within individual protons and neutrons, it also extends between these particles, creating a cohesive nuclear structure. This is achieved through residual strong interactions, similar to how molecules are held together by electromagnetic forces. Although the fundamental strong force acts between quarks, a residual part manifests as an attractive force between protons and neutrons, known as the residual strong force. This force enables the nucleus to stay intact despite the electrostatic repulsion among positively charged protons. The properties of the strong nuclear force make it well suited to its role. It is incredibly strong. It can overpower electrostatic repulsion and highly attractive at typical nuclear distances. Yet, once nucleons are pushed too close, it quickly becomes repulsive, preventing the nucleus from collapsing into an infinitely dense point. This balance ensures stability. Nuclei neither explode apart nor collapse inward. This stability allows for the existence of different elements and the diversity of matter in the universe. Without the strong force, protons would repel each other so fiercely that no stable nuclei beyond hydrogen could form. With it, complex nuclei can assemble, giving rise to elements from helium to uranium, eventually leading to planets, stars, and life. The strong nuclear force also influences nuclear reactions such as fusion and fission. In fusion, lighter nuclei combine under extreme conditions, like in star cores, where the strong force binds them into heavier elements, releasing significant energy. In fission, heavy nuclei split into lighter ones, a process governed by the delicate balance of forces inside the nucleus. In many ways, the strong force is the unseen architect of the universe. It's the reason atoms are stable, and thus matter exists as we know it. From holding protons and neutrons together to forming the universe's diversity of elements, the strong nuclear force functions as a fundamental glue shaping matter's fabric. Though remarkably powerful, it operates over a tiny distance, precisely balancing atomic internal structure. This force exemplifies nature's ingenuity, powerful yet confined to minuscule ranges, enabling the universe's stability and complexity. The weak interaction might sound like a subtle player in the grand story of the universe's birth, but it actually has a crucial role in shaping the very elements that make up everything around us. While it may not be as flashy as gravity or the electromagnetic force, the weak force is essential in driving some of the key processes during the earliest moments of cosmic history. Just after the Big Bang, the universe was a hot, dense soup of fundamental particles, a seething cauldron of quarks, leptons, photons, and other particles flickering in and out of existence. As the universe expanded and cooled, these particles began to combine, forming protons and neutrons, knowingly called nucleons, who would later come together to build atoms. But how did the universe decide whether to favour protons or neutrons? That's where the weak interaction comes into play. In the first few minutes after the Big Bang, the balance between protons and neutrons was dictated by a series of radioactive-like processes driven by the weak force. This force enables certain particles to change types, transforming one into another, by changing their electric charge, which is a unique feature not shared by gravity or the electromagnetic interaction. In this environment, neutrons, which are slightly heavier than protons, would occasionally decay into protons, electrons, and neutrinos via the weak interaction. Conversely, protons could also, under certain conditions, be converted into neutrons. This delicate dance had a profound impact on the ratio of protons to neutrons present in the early universe. As the universe cooled further, these ratios set the stage for the formation of the first nuclei in a process known as Big Bang nucleosynthesis. The resulting proportions of hydrogen, helium, and trace amounts of other light elements depended heavily on how many neutrons survived long enough to join protons and form nuclei. Without the weak interaction, this balance would have been drastically different. If neutrons had decayed too rapidly or not at all, the universe would look very different. Fewer helium nuclei, perhaps more hydrogen, and a very different cosmic landscape. Over time, the weak force helped determine the primordial abundance of elements, setting the chemical foundations for planets, stars, and eventually life itself. It's also fascinating to note that the weak interaction isn't just about the early universe. It continues to play a vital role even today. Processes such as radioactive decay, neutrino interactions, and certain fusion reactions inside stars are all mediated by this subtle force. These ongoing processes influence how stars burn and evolve, shaping the chemical makeup of the cosmos over billions of years. So, in a way, the weak interaction is like a cosmic sculptor, quietly guiding the formation and distribution of elements from the earliest moments of the universe. It's an invisible but indispensable force that has helped craft the universe's chemical fingerprint, one that ultimately leads to the rich complexity we observe today. Absolutely, that's a fascinating thought to explore. The universe, as we understand it, hinges on a delicate balance of physical laws, rules that govern how particles interact, how forces behave, and how matter and energy evolve over time. If those laws had been different, even slightly, the entire story of atoms forming could have taken a very different course, or perhaps not happened at all. Take, for instance, the fundamental constants. Numbers like the strength of the electromagnetic force, the mass of particles like electrons and protons, and ratios such as the balance between the strong nuclear force and electromagnetic repulsion within atomic nuclei. These constants aren't just arbitrary. They're woven into the fabric of physical law, and their specific values allow atoms to exist, to bind, and to create the complex molecules that make life possible. Imagine if the electromagnetic force had been slightly weaker. Protons and electrons, which are positively and negatively charged, rely on this force to come together and form stable atoms. If it had been weaker, perhaps protons wouldn't attract electrons strongly enough to bind into atoms. No light, no chemistry, no the bustling universe of molecules that underpin stars, planets, and life. Conversely, if the electromagnetic force was stronger, protons might cling too tightly or repel each other in unforeseen ways, preventing stable nuclei from forming altogether. Similarly, the strength of the nuclear forces, the forces that hold protons and neutrons together inside atomic nuclei, is crucial. If these forces had been just a little off in strength, atomic nuclei might not have been stable enough to exist. They could have decayed instantly or simply failed to form at all. Such a universe might be filled with only free protons and neutrons, but no complex atoms like helium, carbon, or oxygen, elements that are the building blocks of life as we know it. Not only the strength, but also the ratios of these forces matter. For example, the ratio between the electromagnetic force and the strong nuclear force dictates how easily nuclei fuse or split apart. Slight changes could mean that stars would either burn out too quickly or fail to ignite altogether, preventing heavy element formation. Without these heavy elements being forged in the hearts of stars, the universe would be a very different place, perhaps sterile, lacking planets, and devoid of any environment suitable for life. Even the balance of particle masses influences atom formation. The mass difference between protons and neutrons is finely tuned. If neutrons were a bit heavier, they might decay more rapidly or fail to form stable nuclei. If they were lighter, the process might tilt the universe's chemistry in unforeseen ways, disrupting the formation of complex molecules. And beyond just the constants and ratios, some theories suggest that physical laws might not be immutable in different regions or times. If certain laws varied across space or evolved through cosmic history, the regions where atoms could form might be limited or altogether absent. In some hypothetical universes with altered rules, stable atoms might never have emerged, or they might be very different in nature, creating a universe that's inhospitable to life. To imagine a universe where atoms couldn't form is to picture a cosmos where the very foundations of matter are unstable or incompatible. It's like trying to build a skyscraper on shifting sands. Without stable building blocks, structure collapses. Our universe's precise laws and constants are what create the perfect conditions for atoms to emerge, for particles to bind, and for the rich complexity we see today. So, in essence, the formation of atoms is a delicate dance choreographed by the laws of physics. Slight variations could have led to nothing. No atoms, no chemistry, no universe as we know it. It's a cosmic coincidence, but one that underscores just how finely tuned the universe really is. Once the universe cooled after the Big Bang, the first atoms in the vast cosmic ocean began to find each other. Atoms started to combine, forming the molecules that would become the building blocks of everything around us. The early universe was a hot, dense soup of particles, protons, neutrons, electrons, all colliding and interacting. As it expanded and cooled, these particles found conditions suitable for binding, particularly hydrogen and helium nuclei, which comprised most of the primordial matter. For atoms to form, electrons needed to settle into stable orbits around nuclei, a process governed by quantum mechanics. Electrons exist as probabilistic clouds rather than fixed points, and their energies determine how they can orbit. Initially, many free electrons bounced around at high energies, unable to settle because the universe was too hot and dense. But as expansion continued and temperatures dropped below about 3000 Kelvin, electrons finally combined with protons, forming neutral hydrogen atoms. This process, called recombination, made the universe transparent to light, allowing photons to travel freely, resulting in the cosmic microwave background we observe today. With neutral atoms present, more complex interactions became possible. Unlike individual nuclei, molecules form when atoms share or transfer electrons, creating stable bonds. The most fundamental is the covalent bond, where two atoms share electrons to reach stable electron configurations, often mimicking noble gas stability. For example, when two hydrogen atoms meet, their electrons can pair in a shared orbital, creating a hydrogen molecule. This sharing lowers the system's overall energy, stabilizing the molecule. As the universe continued cooling, nuclear fusion created heavier elements such as carbon, oxygen, and nitrogen. These atoms, with more electrons and bonding possibilities, led to a vast diversity of molecules. These molecules are essential. They form the gases, liquids, and solids that make up stars, planets, and even living organisms. Molecule formation isn't just random collisions. Quantum mechanics influences the likelihood of bonding states. Quantum tunneling allows particles to overcome energy barriers, and electromagnetic forces govern attraction and repulsion. Collisions at the right energies in cooler regions, called molecular clouds, enable the formation of stable bonds. These clouds are star-forming nurseries, where gravity causes gas and dust to cluster, forming dense pockets of matter prepared for further evolution. Within molecular clouds, gravity causes gas and dust to clump together. As regions grow denser, pressure and temperature increase, igniting nuclear fusion in new stars' cores. These stars act as cosmic factories, creating heavier elements in their nuclear cores and dispersing them when they die, through supernova, stellar winds, and planetary nebulum. This dispersal enriches space with atoms and molecules, enabling even more complex structures to form. From simple hydrogen molecules to complex organic compounds, the universe naturally tends toward assembling matter into intricate structures. Every molecule, whether a water molecule in your glass or the carbon chains in living organisms, originates from how atoms bond, an elaborate dance choreographed by quantum physics and electromagnetic forces, spanning billions of years across cosmic distances. Starting from atomic scaffolding, molecules emerge, tiny invisible architects building the universe's intricate tapestry one bond at a time. Each formation moves us closer to the diversity of matter and life itself. The universe, though born from nothing, has an extraordinary capacity to evolve complexity from simple elements, demonstrating an ongoing story of transformation and growth. Word count 593. Electrons may be tiny particles, but their arrangements around an atom's nucleus hold the key to much of the universe's complexity. These arrangements are known as electron shells, and they are fundamental to understanding how atoms interact, bond, and forge the diverse array of matter we see around us. Imagine an atom like a miniature solar system, with electrons orbiting the nucleus much like planets orbit the sun. However, unlike planets, electrons occupy specific energy levels or shells, discrete regions where they are likely to be found. The innermost shell can hold up to 2 electrons, while the next shell can accommodate up to 8, and so on. These shells are not just random zones, they are dictated by quantum mechanics, and the distribution of electrons among them determines the atom's chemical properties. Electrons are more than just orbiters, they are charged particles, and their placement in these shells influences how atoms bond with one another. When atoms come into close contact, their electrons interact, leading to a variety of bonding behaviours. It's crucial to recognise that electrons tend to seek stability. Those outermost shells, often called valence shells, are especially important because they determine an atom's reactivity. Atoms with full valence shells, like the noble gases, are exceptionally stable and usually uninterested in forming bonds. In contrast, atoms with incomplete outer shells will actively seek to fill them. They do this by engaging in different types of bonds. They can share electrons in covalent bonds, transfer electrons in ionic bonds, or form metallic bonds in metals. Covalent bonding involves atoms sharing pairs of electrons to complete their valence shells. For example, in a molecule of water, each hydrogen atom shares its single electron with oxygen, which has 6 electrons in its outer shell. By sharing, all involved atoms reach a more stable configuration, with oxygen having 8 electrons in its valence shell, fulfilling the octet rule, a common principle that atoms tend to have 8 electrons in their outermost shell for maximum stability. Ionic bonding, on the other hand, occurs when electrons are transferred from one atom to another. Think about sodium and chloride. Sodium has 1 electron in its outer shell and readily donates it to achieve a full, stable shell. Chloride gains that electron, completing its own outer shell. This transfer creates charged particles, or ions. Sodium becomes a positively charged ion, while chloride becomes negatively charged. and the electrostatic attraction between them results in an ionic bond, forming common salt. Metallic bonds, characteristic of metals, involve a sea of shared electrons that are free to move around the lattice of metal atoms. This freedom explains properties like electrical conductivity and malleability. The significance of electron shells and bonding extends far beyond simple atoms. They are the foundation for the molecules that make up everything from the air we breathe to the DNA in our cells. By forming different kinds of bonds, atoms create complex molecules with unique structures and functions. These molecules then assemble into tissues, organs, and entire ecosystems. Without the arrangement of electrons in shells and the resulting bonds, matter as we know it would not exist. Crystals, plastics, proteins, each is a product of specific electron arrangements and bonds. It's as if the universe's fabric is woven from countless tiny connections, each governed by the dance of electrons between atoms. Understanding these tiny interactions reveals a profound truth. The universe's complexity emerges from the simple principles of quantum mechanics and atomic physics. From the first hydrogen atom to the complex molecules that sustain life, electron shells and bonding are the scripts that guide the grand story of matter's formation and evolution. They are what turn the raw chaos of particles into the ordered beauty of the cosmos. Atomic number is a fundamental property that shapes the very essence of an element's identity and its behavior in the universe. At its core, the atomic number refers to the number of protons contained within the nucleus of an atom. This tiny numerical signature holds immense power. It determines the element's identity, influences its atomic structure, and ultimately governs its chemical properties. Imagine each element as a unique musical instrument, with the atomic number acting as its tuning fork. Changing the number of protons transforms the instrument into a different entity altogether. For instance, an atom with one proton is hydrogen, the simplest and most abundant element in the universe. Add one more proton and it becomes helium, second in line and essential for the processes that light up stars. Increase the number of protons further, and you progress through this periodic table, each step adding new layers of complexity and potential. The atomic number defines the number of electrons that orbit around the nucleus in a neutral atom, balancing the positive charge of the protons. These electrons are arranged in shells or energy levels, and their configuration dictates how an element interacts with others. The outermost electrons, known as valence electrons, play a pivotal role in chemical reactivity. Elements with a full outer shell tend to behave as inert gases, showing little tendency to react. Those with nearly full or nearly empty outer shells are more eager to form bonds, seeking to reach a stable, full valence shell. This drive to achieve stability shapes the vast diversity of chemical reactions observed. Take lithium, for example, with 3 protons. It boasts a single valence electron, making it highly reactive, especially with elements like oxygen and water. When lithium atoms encounter other atoms, they readily give up this lone electron to form ionic bonds, creating compounds like lithium oxide or lithium hydroxide. This behavior is directly linked to its atomic number and the resulting electron configuration. As you move across the periodic table to elements with higher atomic numbers, the increasing number of protons, and therefore electrons, leads to more complex electron arrangements. These configurations influence element properties such as melting point, density, electronegativity, and atomic radius. For example, noble gases like neon with an atomic number of 10 have complete outer shells, which make them remarkably unreactive. In contrast, fluorine with an atomic number of 9 has 7 valence electrons and a high electronegativity, making it a fierce electron attractor and a powerful reactive agent. Atomic number also influences an element's tendency to form specific types of bonds. Elements with similar valence electron configurations, elements in the same group of the periodic table, exhibit comparable chemical behavior. For instance, alkali metals in group 1 with a single valence electron are highly reactive and tend to lose that electron easily, forming positive ions or cations. Halogens in group 17 with 7 valence electrons are eager to gain 1 electron to complete their outer shell, forming negatively charged ions. Beyond individual atoms, the atomic number subtly orchestrates the chemistry of compounds, dictating how molecules form, break apart, and interact under various conditions. The periodic table itself is arranged primarily by increasing atomic number, revealing patterns and trends in chemical properties that emerge due to changes in the number of protons and electrons. These patterns help chemists predict how different elements will behave, how they might combine, and what kinds of molecules they can form, be it the simple water molecule or complex organic compounds that sustain life. In essence, the atomic number acts as the elemental blueprint, defining what an element is, shaping its electron structure, influencing bond formation, and ultimately scripting the chemistry of the universe. It is a small number with enormous consequences, steering the behavior of matter from the smallest particles to the grandest cosmic structures. In the vast world of atoms and molecules, you might wonder why certain atoms come together to form specific structures while others seem to shun each other entirely. It all boils down to the fundamental forces at play, especially electromagnetism, and the unique properties of each atom. Think of atoms like puzzle pieces. Some fit together perfectly because of their shape, charge, and energy levels, while others just don't align. At the heart of it, atoms are made up of a nucleus, containing protons and neutrons, and a cloud of electrons swirling around. The electrons orbit in regions called orbitals, each with specific energy patterns and shapes. When atoms approach each other, the electrons and nuclei interact through electromagnetic forces, seeking the most stable arrangement possible. This quest for stability determines whether atoms form bonds and what kinds of bonds they will prefer to make. Take hydrogen and oxygen, for example. Hydrogen has a single electron while oxygen has 6. When they come together to form water, the oxygen atom shares electrons with hydrogen atoms, creating covalent bonds. These bonds aren't just random, they're shaped by the way electrons are shared, influenced by how they're attracted to the positively charged nucleus. The resulting molecular structure of water, a bent or V-shape, is the way the electrons settle into the lowest energy configuration for both atoms involved. Different atoms have different numbers of electrons, which in turn influence how many bonds they can form and what geometric arrangements are possible. Carbon, dedicated to forming 4 bonds, prefers tetrahedral arrangements in many molecules because this setup allows the electrons to stay as far apart as possible, minimizing repulsion. This tendency shapes countless organic molecules, from simple methane to complex proteins. But why do particular structures dominate? It's because nature favors the most stable, lowest energy configurations. When atoms bond, they release energy if the new structure is more stable, making those arrangements more likely to happen and persist. Conversely, unstable structures quickly break apart or reorganize into more stable forms. Electronegativity, the measure of how strongly an atom attracts electrons, also influences molecular shapes. Atoms with high electronegativity, like fluorine, tend to pull shared electrons closer, creating polar bonds with partial charges. These partial charges influence how molecules interact, align, and assemble into larger structures. This is why water molecules tend to stick together, forming hydrogen bonds that give water many of its unique properties. The shape of molecules isn't just about aesthetics, it's about how these molecules interact with each other and their environment. Enzymes, membranes, and countless biological structures depend on precise molecular shapes, all dictated by which atoms bond and how they arrange themselves. The specific preferences of atoms for particular bonding patterns and geometries enable the incredible diversity of matter we see. A universe built not at random, but through a delicate dance of forces guiding atoms into their most favourable configurations. In the end, atoms prefer particular molecular structures because those configurations are the most stable, the least energetic, and best suited to fulfill their bonding capabilities. It's this relentless pursuit of stability, driven by electromagnetic interactions, that shapes the very fabric of the molecules forming everything around us. As the universe cooled and expanded over billions of years, the simple atoms that first formed didn't just remain static, they began to come together in intricate ways, laying the groundwork for the rich chemical tapestry we see today. Initially, after the Big Bang nucleosynthesis forged the universe's first hydrogen and helium, these primordial elements were dispersed throughout the cosmos, floating in a vast, hot, and nearly uniform medium. But as gravity pulled these hydrogen and helium atoms into denser regions, they started to clump together, forming the earliest stars and galaxies. Within these stars, the processes of nuclear fusion ignited a fiery alchemy. When a star's core reached immense temperatures and pressures, hydrogen nuclei fused to form helium, releasing energy that lit up the cosmos. But this fusion didn't stop there. As stars lived their lives, burning through their fuel and evolving, they began to create heavier elements like carbon, nitrogen, and oxygen inside their cores. These elements are often referred to as metals in astrophysics, and their formation marked a crucial step toward chemical complexity. When massive stars reached the end of their lives in supernova explosions, these newly forged elements were violently expelled into space, enriching the interstellar medium with a diverse array of elements. The aftermath of supernovae and stellar winds generated enormous clouds of gas and dust, laden with the building blocks for further chemical evolution. These clouds, often called nebulae, could cool and condense under their own gravity, giving rise to new generations of stars and planetary systems. It's within these cooler environments that the next chapter of chemical complexity began to unfold. Atoms and molecules started to interact, bond, and form simple compounds like water, carbon dioxide, and methane. These molecules, though simple by modern standards, were breakthroughs. They introduced stable chemical structures that could serve as the foundation for increasingly complex chemistry. As planetary systems formed, some of these planets and moons had the right conditions. temperatures, presence of water, and energy sources to host even more intricate chemical reactions. Deep within the Earth's primordial oceans, for example, a fascinating and pivotal transition occurred. Certain molecules, through energy from sunlight or hydrothermal vents, combined in ways that laid the groundwork for life's molecular building blocks: amino acids, nucleotides, and other organic compounds. These molecules could then assemble into more complex structures like proteins and nucleic acids, paving the way for the emergence of life itself. But before life, there was a progression from simple to complex chemistry in the broader universe, molecules combining into increasingly sophisticated arrangements. Cosmic dust grains, acting as tiny chemical laboratories, facilitated reactions that wouldn't easily occur in the gas phase. They helped synthesize complex organic molecules, including amino acids and sugars, which have been found not just on Earth, but also in comets and meteorites, suggesting that life's building blocks are widespread across the cosmos. Over billions of years, this ongoing chemical evolution started in the hearts of stars, spread through supernovae, incorporated into planetary bodies, and driven by various physical and chemical processes sowed the seeds of complexity. These processes built a universe rich in diverse molecules, from the simplest diatomic molecules to complex organic compounds. This ever-deepening chemical richness set the stage for life, allowing cells to flourish and diversify, ultimately leading to the astonishing biological complexity we see today. In essence, cosmic chemistry wasn't static. It was a relentless journey from the universe's earliest, simplest elements to a cosmos teeming with complex molecules. Each generation of stars, each planetary system, each molecular interaction bridged the gap from nothing, an initially featureless energy density, to the staggering diversity of matter, molecules, and life that we are fortunate enough to observe and explore. It's a story driven by the fundamental forces of nature and the persistent dance of atoms and molecules across time and space, continually weaving new patterns of chemical richness that form the backbone of everything we see around us. Once the universe had cooled enough for atoms to form, a new chapter in cosmic history began, one driven by gravity's irresistible pull. Tiny atoms like hydrogen and helium started to stick together, drawn by the slightest irregularities in the fabric of space-time. These minuscule density fluctuations, remnants of the quantum wiggles in the early universe, acted like cosmic seeds. Over hundreds of millions of years, these seeds grew into vast clouds of gas stretching across millions of light years. Inside these enormous nebulae, gravity played the role of a master architect, pulling the gas into ever denser regions. As the gas accumulated, the increasing pressure and temperature within these pockets reached critical thresholds. The atoms, previously floating freely in space, began to collide more frequently and with greater energy. Eventually, these interactions sparked the process of nuclear fusion, a power surge that transformed the gas clouds into the first stars. These nascent stars, born from gravitational collapse, ignited nuclear fusion in their cores, converting hydrogen into helium and releasing tremendous amounts of energy. This energy created a luminous glow that pierced through the darkness of the early universe. The birth of stars marked a transition from a universe filled with diffuse gas to a dazzling tapestry of shining points of light. But stars weren't the end of this story. Far from it. They acted as cosmic factories, forging heavier elements in their fiery cores. When massive stars exhausted their fuel, they ended their lives in spectacular supernovae explosions. These violent events blasted freshly made elements like carbon, oxygen, and iron back into space, enriching the surrounding gas clouds with the materials needed to build planets and even life itself. Over time, some of these enriched gas clouds experienced further gravitational collapses, leading to the formation of new generations of stars, each more complex and diverse than the last. Occasionally, planetary systems took shape around these stars as dust particles, consisting of elements like silicon, iron, and carbon, products of earlier stellar processes, coalesced into tiny solid grains. These grains, through a process called accretion, collided and stuck together, gradually forming larger bodies that would eventually become planets. In the dense regions of protoplanetary disks, flattened rings of gas and dust encircling young stars, these particles continued to bump and merge, building up into planetesimals. These building blocks collided repeatedly, growing into planets of various sizes, compositions, and atmospheres. The similarity of chemical signatures across different planetary systems hints at the universal nature of this process, rooted in the fundamental laws of physics and the elements forged in stellar cores. Our own solar system is a prime example of this cosmic ballet. Around 4.5 billion years ago, the protoplanetary disk surrounding the young sun saw particles clumping together, driven by gravity and collisions. Over millions of years, these processes gave rise to the rocky terrestrial planets like Earth, Mars, Venus, and Mercury, as well as the gas giants, Jupiter, Saturn, Uranus, and Neptune. accumulating vast envelopes of gas and ice. The story of how small atoms assembled into stars and planets is written into the very structure of the universe. From the simplest hydrogen atom forming moments after the Big Bang, to complex planets orbiting stars billions of years later, cosmic evolution is a masterpiece of gradual accumulation, driven by gravity's silent but relentless strength. It's a tale of particles, forces, and processes working together across the vastness of space and time, weaving the very fabric of the cosmos we observe today. Once the universe was filled with neutral atoms, mainly hydrogen and helium, these atoms began to come together under gravity. Gravity pulls matter inward, transforming atomic clouds into the diverse worlds we see today. Over millions and billions of years, regions of slightly higher density gathered more matter, becoming denser and hotter. These dense clumps of gas and dust formed the earliest protostars and protoplanetary disks, setting the stage for planet formation. Imagine swirling disks of gas and tiny solid particles orbiting young stars. Within these disks, microscopic dust grains, initially just silicate or carbon compounds, started sticking together through electrostatic forces. As these grains collided and adhered, they formed larger aggregates, pebbles, rocks, and eventually planetesimals, which could be a few kilometers across. These planetesimals competed for material, collided, and merged chaotically, forming larger bodies called protoplanets. Throughout this process, gravity, collisions, and accretion worked together to build planetary cores. The composition of forming planets depended heavily on their distance from the star. In the hot inner regions of a protoplanetary disk, only refractory materials, metals, and silicates could condense and survive, creating terrestrial planets like Earth, Mars, Venus, and Mercury. These planets are mainly solid rock and metal, resulting in hard, durable surfaces classified as solid planets. Farther out, cooler conditions allowed volatile compounds, water, methane, and ammonia to condense. This enabled giant planets like Jupiter and Saturn to develop massive envelopes of hydrogen and helium around solid cores. These gas giants began as rocky or icy cores that grew large enough to gravitationally capture surrounding gases from the disk, resulting in enormous gaseous envelopes that make them primarily gaseous. Icy moons and dwarf planets formed through different processes. They often originated in regions where icy materials could condense and stick together. Some, like Pluto or Europa, are composed of a mixture of ice, rock, and sometimes subsurface liquid layers, maintained by internal heat and gravitational forces. As planets matured, internal heating, generated by radioactive decay, of uranium, thorium, and potassium plus residual heat from formation, caused differentiation. This process involved denser materials, such as iron and nickel, sinking toward the core, while lighter elements like silicates and ices floated outward. Differentiation created layered structures, dense metallic cores, silicate mantles, crusts, or, in gaseous giants, dense cores surrounded by thick atmospheres. The surface states of planets, solid, liquid, or gaseous, are influenced by temperature and pressure. Many terrestrial planets cooled over billions of years, forming solid crusts. These surfaces are reshaped by volcanic activity, tectonics, erosion, and impacts, sculpting planetary landscapes. Planets with liquid surfaces like Earth have enough internal heat and energy to sustain liquid water, an essential ingredient for life. Some moons, such as Europa or Enceladus, harbour subsurface oceans of liquid water beneath icy crusts, maintained by internal heat and tidal flexing from their parent planets. Gaseous planets are dominated by thick atmospheres mainly composed of hydrogen and helium. Their high atmospheric pressure and low temperatures, especially on outer planets, prevent them from solidifying into bulk mass. Their appearances feature rapidly flowing clouds, storms, and complex weather systems that can persist for centuries, Jupiter's Great Red Spot being a prime example. Over cosmic timescales, gravity-driven accretion, condensation, differentiation, and atmospheric retention have shaped planets into their current forms. They represent a transition from simple atomic matter to complex worlds with solid surfaces, liquid oceans, and thick gaseous envelopes. Each planet a record of billions of years of cosmic evolution and artistry. 570 words. The distribution of elements in the universe significantly influences planetary formation, shaping planets' structures, atmospheres, and potential for life. After the Big Bang produced primordial hydrogen and helium, stars formed, lived luminous lives, and ended in supernovae, dispersing heavier elements like carbon, oxygen, iron, and silicon across space, enriching the interstellar medium with diverse materials. When gas and dust clouds coalesce under gravity, the elemental composition of these regions determines what kinds of planets can form. In areas with higher heavy element, metal, abundance. Rocky planets are more common because these metals provide essential building blocks for solid cores and crusts. This is akin to baking bread. More ingredients lead to richer, more complex results. Metal-rich environments foster the formation of dense rocky planets like Earth, Mars, and Venus. Conversely, regions with lower heavy element concentrations tend to produce gaseous planets, primarily made of hydrogen and helium, with only thin solid cores and vast atmospheres. Less metallic environments offer fewer solid particles for planet building, favouring the creation of giant gas planets rather than terrestrial worlds. Elemental distribution also influences planetary characteristics such as size, composition, and internal structure. Planets formed in metal-rich environments often develop substantial iron cores, affecting their magnetic fields, tectonics, and atmospheric composition over time. The abundance of elements like carbon and oxygen influences the presence of water vapour, carbon dioxide, and other volatiles, key components for potential biosignatures. Atmospheric composition is governed by elemental distribution. The proportion of nitrogen, oxygen, carbon, and noble gases in the protoplanetary disk shapes the types of atmospheres planets can develop. Some planets end up with thick, insulating atmospheres similar to Venus, while others possess thin, tenuous ones like Mars or Mercury. These atmospheric features impact surface conditions, temperature regulation, and overall habitability. The distribution of elements also affects moon formation. A planet's composition and nearby icy or rocky debris influence whether it captures or forms moons. Metal-rich planets can generate differentiated moons, which can stabilize the planet's axial tilt and climate, important for maintaining stable environments suitable for life. Beyond individual planets, elemental distribution influences entire planetary systems and their capacity for supporting life. Systems born in regions with high metallicity, rich in heavy elements, are statistically more likely to produce habitable planets. This correlation is important in the search for extraterrestrial life. The greater the availability of metals, the higher the chance of forming diverse, potentially life-supporting worlds. Differences in metallicity, star type, and star formation history create a complex mosaic of planetary environments across the galaxy. From scorching worlds close to their stars to icy bodies in the outer regions, initial ingredients provided by the cosmic neighbourhood determine which planets can emerge and how they evolve over millions or billions of years. As we examine distant worlds with telescopes and analyse their atmospheres, we are reading the elemental blueprint from which these planets originated. Each planet's story is embedded in its elemental composition, reflecting how the distribution of atoms shapes the universe's rich tapestry of worlds. This distribution isn't random. It's a crucial factor in the ongoing story of planetary creation, an evolving narrative unfolding across the cosmos. The cosmic distribution of elements is key to understanding why some planetary systems are more diverse than others. Variations in metallicity, star types, and star formation histories generate a wide array of planetary environments, from hot, close-in worlds to icy bodies in distant orbits. These initial conditions set the stage for how planets form, evolve, and potentially support life over extensive periods. Studying the atmospheres and compositions of planets helps decode their origins and the raw ingredients that influence their development. Every planet's unique makeup narrates its formation history, offering insights into the fundamental processes governing planetary diversity. Variations in elemental distribution impact planetary characteristics, surfaces, atmospheres, and habitability. In sum, the distribution of elements across the universe acts as a cosmic blueprint in forming planetary diversity. It governs the types of planets that form, their internal structures, atmospheres, and viability for life, shaping the planetary landscape of the cosmos. The ongoing study of elemental distribution continues to uncover the intricate links between cosmic chemistry and the emergence of worlds capable of supporting life, demonstrating the fundamental importance of element distribution in planetary evolution. As the universe continued to expand and cool, it was no longer just a vast, featureless expanse filled mainly with hydrogen and helium. Instead, tiny variations in density laid the groundwork for something extraordinary: the emergence of complex structures like stars, galaxies, and eventually planets, and even life itself. The seeds of these marvels were not just planted by the gentle pull of gravity, but also by violent cosmic collisions and the gradual process of accretion. Imagine the early universe, a chaotic playground where clouds of gas and dust began to swirl and clump together. Gravity, the silent sculptor, pulled these particles inward. As regions grew denser, they started to attract more matter, creating the first protostars and proto-galaxies. But it wasn't a smooth journey. Instead, it was marked by dramatic collisions, massive clouds crashing into each other at enormous speeds, sometimes causing shock waves that heated and compressed the gas. These colossal impacts acted like cosmic pressure cookers, igniting nuclear fusion in newly forming stars or dispersing gas clouds, which then traced a new pattern under gravitational influence. In these turbulent environments, accretion, the process of matter slowly spiraling onto a central object, became a key player. Picture a young star or planetary core gathering surrounding gas, dust, and even larger debris, growing more massive with each collision and accretion event. Over millions of years, this relentless feeding frenzy built up dense, luminous stars. The energy released during these processes often led to outbursts that cleared away surrounding material or triggered the formation of new stars, demonstrating how interconnected and dynamic cosmic evolution could be. When two stars or planetary bodies collided, the energy released could dramatically reshape their surroundings. Sometimes collisions were destructive, vaporizing planetary surfaces or star systems, but other times they sparked the creation of new worlds. Planet formation itself was driven largely by accretion, tiny dust particles sticking together, forming centimeter-sized pebbles, then kilometer-sized planetesimals, which further collided and